Knowledge Products presents Science and Discovery, narrated by Edwin Newman. This is On Medieval Science.
From the fall of Rome in 455 AD until intellectual life began to revive after 1000 AD, Europe endured a long drought of ideas. For more than 5 centuries there was little measurable progress in scientific and philosophic understanding in Europe. Indeed, there was a dramatic loss in many areas of inquiry. The classical beginnings of natural science, particularly the work of the ancient Greeks, was largely lost in Europe. These years would later become known as the Dark Ages of European history. The Romans were partially responsible for the decline. They were mostly uninterested in questions about the nature of physical reality, questions that had so moved the Greeks. But even more of the responsibility must be laid at the door of the established Christian Church. Christian officials during the entire Middle Ages often tended to view science and all independent inquiry as potentially heretical. The historian Sir William Cecil Dampier has described how the Church and its patrician leaders affected secular intellectual progress.
Much patristic and early medieval Christianity was inimical in spirit to secular learning. Under its influence, philosophy became the handmaid of theology, and natural science vanished from the earth.
The Dark Ages are often embedded by historians in the longer period called the Middle Ages, which continued until around 1500 AD. This 1,000-year interval spanned the time between the classical world and our own modern era, from the world of the ancient Greeks and Romans to the Renaissance. Thus, both the Dark Ages and the Middle Ages are names that emphasize the effect of an age on European civilization. While it may be an exaggeration to claim that natural science vanished from the earth during the Middle Ages, progress in scientific understanding is certainly easy to miss during this time, especially if one looks only at developments in Europe. The obstruction of European science and reason during the Dark Ages did not mean that all progress simply stopped. Even in Europe, many developments would prove vital to the expansion of human understanding. For example, the so-called barbarians periodically overran Europe, bringing new techniques and ideas that were adapted and made part of common European life. But most important were developments in the Arab world. For most of the Middle Ages, human understanding and progress was centered in Arabia, and our science owes an incalculable historical debt to the Arabs. As we'll see, it isn't just that the Arabs preserved ancient European works while they were burned or otherwise lost in Europe, although this alone is stunningly important. And it isn't just that Arabian centers of scholarship embraced Chinese and Indian ideas, although without them our modern mathematics would have taken much longer to develop, if at all. As important as these contributions may have been, they're far from the whole story. Modern science is as much an Arab invention as a European one, and the contributions of Asian thought gained much of their relevance because of the way Arabs applied them. The story of medieval science is one of excitement and conflict, loss and tragedy, the story of rising and falling civilizations and institutions. To tell this story well, we must tell it from the beginning. There has long been controversy about the basic causes of the decline and fall of the Roman Empire, but the symptoms pointing toward dramatic change were fairly clear for a long time. Edward McNall Burns offers a compelling sketch of the situation near the end of Europe's so-called classical period of history.
During the period from 284 to 476 AD, Roman civilization was strongly influenced by a revival of Oriental ideals of despotism, otherworldliness, pessimism, and fatalism. In the midst of economic distress and cultural decay, men lost interest in earthly achievement and began to yearn for spiritual blessings in a life after death. This change in attitude was due primarily to the spread of Oriental religions, especially Christianity. When the Roman Empire finally collapsed, the victory of Orientalism was almost complete. The result was the evolution of new civilizations, compounded in part of elements taken from Greece and from Rome, but with religion as a dominant factor behind most of their achievements.
The collapse of Roman power was eventually to lead to three new and distinct cultures: the Byzantine civilization, the civilization of Western Europe, and the Muslim or Saracen civilization. The last of these, the great civilization of Islam, did not emerge until the 7th century, but it played a very important role in the story of medieval science. The Roman Emperor Constantine had formally ended the official persecution of Christians in a series of edicts issued in 313, the most important of them called the Edict of Milan. All of these edicts protected Christians in the same way that pagan cults had been protected by law. In 330, Constantine established a new imperial capital at Constantinople, on the site of the ancient city of Byzantium. For what appear to be largely political motives, his policies by that time had begun actually to favor Christianity. But with Constantinople as the new seat of empire, the decline of Rome began in earnest. The growing influence of Christianity in the Old Empire became even more explicit when Emperor Theodosius I decreed that every Roman subject must become Christian. A short time thereafter, a second decree officially classified paganism as treason. Theodosius was the last ruler of the unified Roman Empire. The empire had, from time to time, been divided into from 2 to 4 administrative regions. Upon the death of Theodosius in 395, the division between East and West became permanent. One of Theodosius's sons, Arcadius, became emperor in the East. Another son, Honorius, became emperor in the West, establishing his capital at Ravenna rather than Rome. But real power and prestige were already shifting to Constantinople, and Rome went into rapid decline. In 410, the Visigoths, a Germanic tribe in revolt against oppression by their Roman governors, marched into Rome under the leadership of Alaric. They ransacked the city for 3 days and then left. Public disorders increased within Rome. Roman citizens themselves took to stripping buildings and monuments of their marble. Romans raided public places for anything of value. Indeed, it appears that, during these years of the early 5th century, Romans did more damage to the city than invaders did. In 455, a second invasion, this time by Gaiseric and the Vandals, led to 2 weeks of pillage. To many historians, this second invasion marked the unofficial end of Rome's influence. The population of the city, which had once been well over 1 million, had already sunk to 250,000. In the next years it was to plunge yet further, to less than 50,000, where it would stay for most of the Middle Ages. The official end of the Western Roman Empire occurred in 476, when Romulus Augustus, the last emperor in the West, was deposed by Odoacer and the Goths. Both the fall of Rome in 455 and the end of the Western Empire in 476 were potent symbols that the Dark Ages had begun in the politics of Western Europe. Yet the event that offers the defining intellectual symbol of the beginning of the Dark Ages occurred, as we'll see, at the Library of Alexandria in Egypt. The city of Alexandria had been founded in 332 B.C., about 800 years before Rome's fall, by Alexander the Great of Macedon. After studying as a boy under the Greek philosopher Aristotle, Alexander succeeded to his father's throne and soon conquered an impressive portion of Europe, Africa, and Asia. These conquests began what has become known as the Hellenistic period in world history. The historian Sir William Dampier in 1942 eloquently summarized the influence of Hellenism.
With the marches of Alexander the Great, we reach a new epoch. He carried to the east that Greek culture which was already spreading westwards over the Mediterranean, and in return he brought Babylonia and Egypt into closer touch with Europe. Thus began 3 centuries of Hellenism, from the death of Alexander in 323 BC to the establishment of the Roman Empire by Augustus in 31 BC, centuries during which Greek culture, having passed its zenith in its original home, spread to other lands and dominated the known world. A form of Greek language, the common speech, was understood from Marseille to India, from the Caspian to the cataracts on the Nile, and the upper classes, from Rome to Asia, accepted Greek philosophy and the Greek outlook on life. Commerce became international, and thought was free as it was not to be again till recent days.
As Stephen Mason has observed, the history of science and technology was particularly changed by this new historical period.
On all of his campaigns, Alexander took with him engineers, geographers, and surveyors. Such men mapped out the conquered countries and noted their resources, collecting a vast store of observations on natural history and geography. Theophrastus made use of the observations on plants in his botanical works, whilst another of Aristotle's pupils, Dicaearchus, made use of the geographical information to make a map of the known world. Dicaearchus was the first to draw a line of latitude across a map, the line running from the Straits of Gibraltar along the Taurus and Himalaya ranges to the Pacific Ocean.
Alexander's conquests took his armies, along with inquisitive surveyors and geographers, as far east as India. New information flowed in torrents back to Greece, where it encouraged a shift from abstract and speculative philosophical thoughts to a new, more empirical way of thinking. Geographic and biological material was not all that was shipped back. The conquest of Mesopotamia in 331 BC yielded the rich details of Babylonian astronomy and mathematics. All this new knowledge was sent home to Greece. Returning from conquests much farther east, Alexander died of fever at Babylon in 323 BC, and his empire soon dissolved. Egypt was seized by one of Alexander's generals, a man named Ptolemy. Like Alexander, Ptolemy had studied with Aristotle as a youth, and his commitment to learning led him to establish the world's greatest center of learning in Alexandria. Ptolemy hired Strato of Lampsacus, who would later direct Aristotle's own school, the Lyceum, to help him found the museum. Strato gathered 100 professors, along with written documents and research data from all over the world. Ptolemy's Egyptian government thus turned the Alexandrian Museum into the first large-scale public university in history. The prestige of the professors, along with the importance and novelty of the materials they studied, soon shifted Europe's intellectual center from Athens to Alexandria, beginning in about 300 BC. There were 4 departments at the museum: literature, mathematics, astronomy, and medicine. The library, with somewhere between 400,000 and 700,000 scrolls in its collection, became by far the largest library ever known in the ancient world. Ptolemy's ambition was to house all of the works ever written. Scrolls were borrowed from Athens, and the great works of Greek philosophy and science were copied. 70 Jewish scholars were gathered together in about 250 BC to translate Hebrew scripture, what we now call the Old Testament, into the Greek language used in Alexandria. Their work is called the Septuagint, from the Greek word for 70. This high standard of scholarship is the way things stood for about 700 years. Political and artistic leadership moved to Rome, and scientific activity was largely centered in Alexandria. Meanwhile, Christianity had become influential. Its doctrine that the day of judgment was near suggested that the things of this world are not so important. St. Ambrose of Milan expressed it succinctly.
To discuss the nature and position of the earth does not help us in our hope of the life to come.
Christian doctrine fundamentally opposed scientific concerns, and Christianity became more powerful as it became the state religion of the Roman Empire. Then a series of events in Alexandria foreshadowed the Dark Ages in Europe. Much of this history was poorly recorded and not well understood, but apparently the Alexandrian library was seriously damaged and perhaps partially destroyed in a civil war in northern Africa during the 2nd century. In 390 A.D., Bishop Theophilus torched an entire section of the library. By 640 A.D., after Alexandria was conquered by Islam, the rest of the collection was demolished. It's not certain whether this final Islamic destruction of the library was deliberate or accidental. What is plain, however, is that the demise of the museum and its remarkable library was a potent symbol of the spirit of the times. Greek science fell before the spiritual emphasis now spreading steadily across Europe. There were other tragedies. In 415, a Christian mob barbarously murdered Hypatia. She was the daughter of the astronomer Theon, and is known to history as the last mathematician of Alexandria. Tradition has it that the mob was incited by the Archbishop of Alexandria, a man also responsible for driving the Jews from that city. The bishop was later canonized as St. Cyril. Ironically, one of the last Alexandrian contributions to classical science was made in the context of Christian theology. The Church had adopted an amalgam of Neoplatonic, Aristotelian, and Ptolemaic cosmology, the latter named after Claudius Ptolemaeus, the great Alexandrian mathematician and geographer of the 2nd century A.D. According to this cosmological synthesis, the universe consists of a graded chain of beings. These beings are ranked, beginning with the basest inhabitant of hell, at the center of the earth, and thus at the center of the universe. The chain of beings extended all the way out to the prime mover, God, who moves at the periphery of the cosmos. This cosmology said that God is needed at all times to keep the heavens moving. The heavens, in turn, keep everything else going, all the way down to the earth's center. Ioannis Philoponus, a 6th century Alexandrian, insisted that there is no need for God to continue to influence things to keep them in motion. He said that once an impetus had been imparted to a thing, the object will naturally tend to continue in motion until something stops it. Philoponus of Alexandria was branded a heretic by the Church. His ideas about motion were not to become influential for more than 1,000 years, when Galileo and Isaac Newton convinced the world that this concept of motion is the correct one. The Alexandrian period was a transition time between the ancient world and the Middle Ages, and in Alexandria more than anywhere else, the Greek tradition encountered the Middle East. Sir William Dampier has described what happened.
At Alexandria, a school of thought arose, influenced on the one hand by Hellenistic culture, and on the other by Jewish and Babylonian tradition. It must be remembered that but a small and relatively unimportant number of the Jews returned to Palestine at the end of the Babylonian captivity, while many of the remainder established themselves as traders in the cities of Asia Minor and the Levant, and formed a network of communication, commercial, political, and intellectual, throughout the East. Alexandria became the commercial and intellectual center, while Jerusalem remained the religious center of this scattered community. And for this reason, Alexandria was the first important meeting ground between Greek philosophy and Oriental religions, especially Judaism and Christianity. Many of the early Greek fathers of the Christian Church lived at Alexandria or drew their philosophy therefrom. It was by their means that much Greek philosophy retained its vitality and took its place in that synthesis of Jewish, Greek, and Christian thought which went into the composition of patristic theology. The ideas of Plato, and to a lesser degree those of Aristotle, thus passed into early Christian theology and became current in medieval Europe long before their origin was suspected by the churchmen.
Here Sir William Dampier has in mind the perspective of the churchmen of the 11th and 12th centuries, who had no idea that Christian doctrines were related to Greek philosophy.
When Greek authors were afterwards rediscovered, the churchmen were amazed to find the prototypes of familiar Christian doctrines embedded in the works of heathen philosophers.
After the fall of Alexandria, some Christian officials began to reject the Greek view that the earth is spherical. The historian Stephen Mason describes what happened.
With the rise of Christianity came a revival of the Bronze Age theory that the earth was flat, supported by waters beneath and covered by waters in the vault above. Such a view had an appeal for some of the early church fathers, who considered that the universe was analogous in general configuration to the tabernacle. The flat earth theory was supported the most strongly by the Syrian church, notably by Cyril of Jerusalem and Diodorus, bishop of Tarsus, the latter going so far as to declare that the Greek system of the world was atheistical.
Greek knowledge was not simply lost, it was often hidden or deliberately destroyed. Secular knowledge became a dangerous thing, but there were exceptions, even within the church. St. Ambrose believed in the 4th century that questions about the nature and position of the earth are not very important, yet he remained partial to the Greek belief that the earth is a sphere, suspended under the spherical vault of the heavens. St. Augustine, a disciple of Ambrose, shared a similar view. Isidoro, the Spanish bishop of Seville, spoke tolerantly of ancient Greek science in his influential 7th century encyclopedias called Etymologies. Isidoro himself apparently preferred the view that the earth is like a wheel, surrounded by ocean, and placed in the center of several moving heavenly spheres. A 7th and 8th century Benedictine monk named St. Bede of England, whose great scholarship earned him the historical name the Venerable Bede, saw the earth as Isidoro did. Incidentally, Bede's great influence was largely responsible for the modern Western custom of dating events from the birth of Christ. Both Bede and Isidoro emphatically rejected the idea that there could be inhabitants of lands called the Antipodes. These were regions that might lie beyond the encircling ocean, which they imagined as surrounding Europe, Asia, and the northern portions of Africa. St. Augustine had already pointed out in the 5th century that any belief in inhabitants of the Antipodes is inconsistent with Scripture. How, for example, could antipodal human beings, cut off from the rest of the world, be descended from Adam? Even where the general ideas of classical astronomy were preserved in Europe, the details were largely lost. Isidoro's Etymologies, written in the first few decades of the 7th century, preserved only some of these details. The Etymologies became one of the most widely read overviews of scientific knowledge in Europe for 1,000 years. They provide an excellent guide to the way the universe was understood by the best and the brightest minds of the Middle Ages.
The sphere of the heavens is rounded, and its center is the earth, equally shut in on every side. The philosophers have brought in the theory of 7 heavens of the universe, that is, planets moving with the harmony of the spheres. The sphere of heaven, moving from the east towards the west, turns once in a day and night in the space of 24 hours, within which the sun completes his swift revolving course over and under the earth. With such swiftness is the sphere of heaven said to run, that if the planets did not run against its headlong course in order to delay it, it would destroy the universe.
With considerable reserve, Isidoro also reported such ancient Greek curiosities as the atomic theory of matter.
The philosophers call by the name of atoms certain parts of bodies in the universe so very minute that they do not appear to the sight nor admit of division, whence they are called atoms. These are said to flit through the void of the whole universe with restless motions, and to move hither and thither like the finest dust that is seen when the rays of the sun pour through the windows. From these, certain philosophers of the heathen have thought that trees are produced, and herbs and all fruits, and fire and water, and all things are made out of them.
The Greek schools that had been founded in Athens during the 4th century B.C., the Academy of Plato and the Lyceum founded by Aristotle, were closed by the Roman Emperor Justinian in 529 A.D. But by then even the Academy had begun to teach a rather mystical combination of Platonism and Christianity, as the historian Sir William Dampier explains.
The modes of thought inaugurated by Plato were wafted into even more super-rational heights by the Neoplatonists, whose philosophy was the last product of late paganism. Philosophy became less and less physical and experimental, and more concerned with mystical ideas. Plotinus the Alexandrian lived in a pure region of metaphysics warmed with occasional ecstasy, and to him the highest good was the super-rational contemplation of the absolute. In the writings of Porphyry, and still more in those of Iamblichus, these mystical views were brought down to practical life, and their application thereto led to greater credulity in magic and sorcery. The soul needs the aid of God, angel, demon. The divine is essentially miraculous, and magic is the path to the divine. Thus, Neoplatonism countenanced and absorbed every popular superstition, every development of sorcery and astrology, and every morbid craving for asceticism, of which a decadent age was prodigal.
Justinian, wielding the power of the state, seems to have closed the famous independent Greek schools in order to destroy the last remaining centers of heathen philosophy. The officially recognized Christian schools now had fewer competitors. The doors to science were closing all over Europe. Rome still had barbaric traditions and customs, like divining the future by examining the livers of animals. Stephen Mason has explained the matter in this way.
The Romans, like the Greeks, came to civilization during the Iron Age, directly from barbarism. However, they did not get away from the traditions of the Bronze Age so completely as the Greeks. Rome was a warrior agriculturalist community, like Sparta, the least intellectual of the Greek states. Commerce was forbidden to the senators of Rome, whilst her merchants submitted to the values of their society, aspiring to become the owners of farming land. The Romans, therefore, lacked, above all, the quantitative and spatial thinking of the merchant traveler, rendering them weakest in the mathematical sciences.
At the peak of Roman civilization, in the 1st century B.C., even Cicero had pointed out Roman weakness in the sciences.
Greek mathematicians lead the field in pure geometry, while we limit ourselves to reckoning and measuring.
The Romans never produced any mathematicians or astronomers of note. There was only one important Roman geographer, Pomponius Mela, who lived in the 1st century A.D. Mela adopted much of the approach of his brilliant Greek predecessor Eratosthenes, who had calculated the circumference of the spherical Earth as about 24,000 miles in the 3rd century BC. But even this lone Roman geographer carefully avoided the mathematics and measurements that stood out so clearly in Eratosthenes' earlier work. Romans did make some contributions, for a while at least, in medicine, but by the time Rome fell, even this had deteriorated. The great 16th century Belgian professor of medicine, Andrea Vesalius, who taught in Padua, wrote in 1543 about the decline of ancient Roman medicine.
The more fashionable doctors began to delegate to slaves the manual attentions they judged needful for their patients, and themselves merely to stand over them like architects. Then, when all the rest who practiced the true art of healing gradually declined the unpleasant duties of their profession, without, however, abating any of their claim to money or to honor, they quickly fell away from the standard of the doctors of old. Methods of cooking and all the preparation of food for the sick they left to nurses. Compounding of drugs they left to the apothecaries. Manual operations to the barbers.
Most people today regard alchemy as the misguided efforts of medieval mystics who tried to use magic to turn tin into gold. The historian Bert Hansen has emphasized a central misunderstanding that pervades the modern view of the Middle Ages.
The medieval world has long been associated with magic. Merlin with his wand, and witches toiling over their cauldron are standard props in the conventional picture of the Middle Ages. This popular image is generally correct in seeing that age as fostering the occult, but it needs to be refined in one important respect relating to medieval science. In the Middle Ages in Western Europe, magic was not an obscurantist superstition, hostile to scientific rationality, nor was it a challenge or even an alternative to science. This contrast arose only in modern times.
The modern stereotype of medieval alchemy is especially misguided. Alchemy was essentially the earliest effort to develop the chemical sciences, and it was firmly based in the Platonic philosophy that prevailed at the time. One goal was to find the chemical properties that would permit one substance to be converted to another, such as a base metal to gold. Other goals included finding a universal cure for disease, and to find the secret of indefinitely prolonging life. Seen in this light, most would agree that the alchemists were pursuing worthy and enduring scientific goals. The practice of alchemy began at a time and in ways that are not completely clear. There is reason to believe that alchemy was practiced in ancient Egypt before 2000 BC, but there are conflicting historical hints that alchemy may have arisen much later in China, sometime between the 5th and 3rd centuries BC. It may have been brought westward from there. Historians disagree about the origins of alchemy, partly because they don't agree on exactly which practices characterize alchemy. In any case, there's no doubt that alchemy began to flourish by the ancient Hellenistic period, especially in Alexandria. According to the historian Sir William Dampier, this increasing importance of alchemy was linked to efforts to produce cheaper imitations and substitutes for expensive objects.
In the preceding centuries, there had arisen in all Mediterranean countries an industry derived from early chemical processes which supplied imitations of things too expensive for the people. Imitation pearls, cheap dyes which matched the costly Tyrian purple, alloys which looked like silver and gold, all became articles of commerce.
Alchemy also borrowed considerably from areas, such as astrology, that were somewhat less pragmatic and more theoretical.
Alchemy, from an early date, was linked with other prevailing realms of thought, and particularly with astrology. The sun, which vivifies all nature, generates gold, his image or antitype, in the body of the earth. The white moon represents silver, Venus, copper, Mercury, quicksilver, Mars, iron, Jupiter, tin, and Saturn, farthest and therefore coldest of the 5 planets, the heavy and dull metal lead.
As it was practiced in the Hellenistic world, alchemy owed a considerable theoretical debt to classical Greek philosophy, and especially to Plato. According to Plato's theory of forms, the particular things encountered in daily life are actually less real than the forms or categories they exemplify. For example, a particular lump of copper was understood to be less real than an ideal form or concept of copper. This is because the only things that can be known about any lump of copper must depend upon what's known about that metal's general form. What is knowable, according to Plato, always involves the forms or ideas of things, that is, their category. This doctrine was easily applied to Plato's understanding of humanity. Human beings are not to be understood in terms of the physical matter that makes them up, but rather in terms of their form or idea, which of course is an abstraction. In the case of a human being, this abstract form is the human soul. Following this reasoning, the human soul was held to be more real than the human body. Indeed, Platonists said a human being is an abstract, immaterial soul. The human body is mere matter, neither knowable nor fully real. This is all related to alchemy because alchemists believed we find the real nature of metals in the same way we find the real nature of humanity. Alchemy ultimately derives not only from Plato's theory of forms, but also from Aristotle's ideas about the relation between substances and their qualities. According to the alchemists, the essence of metals is no more related to their physical matter than the human soul is related to the body. All physical things, including human bodies, are merely material objects. So, in a sense, their material construction is all the same. The differences between any physical objects are differences in form. These are differences of abstract qualities, not of physical matter. So, the alchemists believed that if they changed the qualities or properties of something, they could change the thing itself, just as changing a person requires altering the person's character, not his or her body. What's more, the alchemists thought the soul or spirit of the metals is expressed best in their color. So, learning to change copper in a way that gives it the color of gold is to transmute it to gold. The German Dominican monk Albertus Magnus tried to explain the art of alchemy to his Christian brethren in the 13th century. He explained the next step in alchemical reasoning as follows.
Metals differ from one another only in their accidental form, not in their essential form. Therefore, the stripping of accidents in metals is possible. Hence, it is also possible through this art to bring about a new body, since all species of metals are produced in the earth from a commixture of sulfur and quicksilver, or because of fetid earth.
The issue is not just a matter of surface color. Painting a lump of copper with gold paint doesn't transmute it. What's needed is a deeper, chemically generated change. This is the process that so impressed the alchemists, and their attempt to understand the essential character of metals is why alchemy is so important in the history of chemistry and metallurgy. According to Sir William Dampier, we can best understand the Alexandrian alchemist as a kind of experimental scientist.
In practical alchemy, 4 steps were usually indicated. 1. Tin, lead, copper and iron were fused together into a black alloy in which each had lost its individuality and mingled in the oneness of Plato's first matter. 2. Mercury, arsenic, or antimony was added to whiten the copper and thus simulate silver. 3. A ferment of a little gold was then given, and the white alloy treated with sulfur water, that is, calcium sulfide or mordant salts. Thus the alloy acquired the color of gold. Indeed, to the Alexandrian alchemist, if a metal was given yellow color and sheen, the essential qualities of gold, it became gold. Unlike some of his successors, the Alexandrian alchemist was neither a fool nor a charlatan. He was experimenting both in science and in art, in conformity with the best philosophy of his age.
Even in today's subatomic theories, scientists continue to use the hypothesis that there is a basic general stuff out of which everything else is made. The distinctions between different things are believed to involve different configurations of the basic stuff. A modern example is the theory of quarks and leptons in modern physics. It says that all things are made of atoms, that all atoms are constructed out of various arrangements of subatomic particles, and that all such particles finally are composed of quarks, leptons, and their antiparticles. Another modern example that helps to explain Plato's theory of forms is the frequently repeated doctrine that science has nothing to say about singularities. These are one-of-a-kind events, such as the Big Bang, which supposedly occurred at the beginning of the universe. Scientists cannot study singularities because they can't be the subject of repeated experiments. Scientists can only reason that a singularity behaves like other objects in the same category or class of things. This is very similar to the Platonic idea that we cannot know individuals except as they partake in or imitate forms. The alchemists were not studying singularities, but they did study whole classes of things to find concepts or forms that would address the problems and ambitions of their day. This more or less scientific approach to alchemy began to decline amid increasing hostility towards secular knowledge. Even before Bishop Theophilus torched Alexandria's library in 390, the Roman Emperor Diocletian, hostile to anything he deemed non-Roman, apparently ordered the alchemists' books to be burned in 292. Alchemy was forced underground, where it was practiced less and less. Alchemy now became more mystical and less experimental, and it would make its way down through the centuries in the form of a mystery. By the 12th century, alchemy was becoming influential in Europe. In the 13th century, Albertus Magnus treated alchemy as a mystery when he urged secrecy and exclusiveness in pursuing this special art.
I purpose to write for my associates and friends the true art, clear and free from error. However, in such a way that seeing they may not see, and hearing they may not understand. Therefore, I beg and I adjure you by the Creator of the world to hide this book from all the foolish. For to you I shall reveal the secret, but from the others I shall conceal the secret of secrets because of envy of this noble knowledge. Fools look down upon it because they cannot attain it. For this reason they consider it odious and believe it impossible. They are therefore envious of those who work in it and say that they are forgers. Beware, then, of revealing to anyone our secrets in this work. A second time I warn you to be cautious. Persevere in your labors, and do not become discouraged, knowing that great utility will follow your work.
During the Dark Ages, and even into the first centuries of the medieval period, we've seen that interest in science was limited by the Church's hostility to secular learning and by lost contact with the works of classical science. It was limited also by a third, more practical difficulty, a non-rational view of what it meant to be educated. In the Middle Ages, to be educated was to be a man of the cloth. Education was available only through the monasteries, which produced only clerics. These men considered themselves to be specialists in spiritual knowledge rather than worldly knowledge. At best, their regard for questions of science was that of interested amateurs, as the historian A.C. Crombie has observed.
The learning of Western Christendom was predominantly theological and moral. The early Christians at first tended to disparage the study of philosophy itself as likely to distract men from a life pleasing to God. St. Clement of Alexandria, in the 3rd century, poked fun at this fear of pagan philosophy, which he compared to a child's fear of goblins. And both he and his pupil, Origen, showed that all knowledge was good, since it was a perfection of mind, and that the study of philosophy and of natural science was in no way incompatible with a Christian life. St. Augustine himself, in his searching and comprehensive philosophical inquiries, had invited men to examine the rational basis of their faith. But in spite of these writers, natural knowledge continued to be considered of very secondary importance during the Dark Ages.
Nature was studied not to understand the natural world itself, but to understand the lessons of Christianity. Scientists wanted to know how natural things might have symbolic or magical powers that can affect human life. According to A.C. Crombie,
preoccupation with the magical and astrological properties of natural objects was, with the search for moral symbols, the chief characteristic of the scientific outlook of Western Christendom before the 13th century. It was a very general belief during the whole of the Middle Ages, and even into the 17th century, that there was a close correspondence between the course of a disease and the phases of the moon and movements of other heavenly bodies.
It's not a simple matter for the modern mind fully to understand what people in the Middle Ages meant when they described something as natural or magical. They used the word natural to designate things that are normal or usual. Anything out of the ordinary would have been called unnatural or preternatural. The historian Bert Hansen has explained the matter well.
An event might be considered outside of nature or preternatural if it were rare enough. For example, monstrous births, such as a two-headed calf, were not then regarded as natural, although from our point of view, deviations from the normal course are nonetheless governed by natural laws and processes.
Machines and other artificial contrivances were placed in the category of the preternatural rather than among the natural phenomena. The 17th century commentator Tommaso Campanella, looking back at the Middle Ages, offered specific examples.
Everything done by skilled men in imitating nature or helping it by unknown art is called magical work, not only by vulgar crowds, but by all men in general. It was considered magic when Archytas made a dove which could fly like a natural one, and at the time of the Emperor Ferdinand in Germany, a German constructed an artificial eagle and a fly which flew by themselves.
The tools of the magician, then, were rules, recipes, and procedures that had specific effects in the realm of the preternatural. Modern scientists reject the realm of the unnatural as unreal. But for the people of the Middle Ages, the unnatural or preternatural was simply unusual, something that only those with specialized knowledge could manipulate. Today's scientists, engineers, and even manufacturers can manipulate the world in such a specialized way. They produce things or effects that would have been called preternatural in the Middle Ages. They are the modern magicians. Medieval magicians were involved with some things that to us are stunningly fanciful, yet they also were concerned with other things that we would judge to be quite practical. Some magical practices were designed to have real effects, and others were plainly intended to produce what we would call illusions. For example, the English poet Geoffrey Chaucer in the 14th century told the story of a cleric with magical powers. He was hired by a suitor who wanted help in pursuing a woman named Dorigen. The young man's advances were unwelcome, so Dorigen told the young man that she might look favorably on him if he cleared all the rocks from the shores of Brittany. The suitor now wanted the cleric to use his magic to convince Dorigen that he had cleared these rocks.
The skilled cleric worked night and day, doing all that was possible to arrive quickly at the results of his astrological computations. That is to say, to bring about an illusion by some juggling appearance, so that Dorigen and everyone would think and say that the rocks had either gone away from Brittany, or else that they had sunk underground. At last he arrived at the proper time to work his tricks and magic in that cursed superstitious manner. He brought out his astronomical tables from Toledo, carefully corrected. He lacked nothing, neither his tables for short periods of years, nor those for longer periods, nor his roots or other mathematical gear, such as his centres, his quantities, and his tables of proportions for all sorts of equations. He calculated all these things very expertly. He was quite sure that the moon's mansion was favourable for his operation, and he knew all the other details to be observed in order to produce such illusions and evil tricks as the heathen people practised in those days. Therefore, he waited no longer, but as a result of his magic, it seemed for a week or two that all the rocks had disappeared.
Just what had the magician accomplished? The answer is not at all clear from the story. In the same way, it's not at all clear what the medieval understanding of magic achieved for those who believed in it. Islam was born in Mecca on the Arabian Peninsula during the year 610. When the religion's founder, Muhammad, died in 632, he left the Arab state leaderless. Then, in 661, an Arab family called the Umayyads won the struggle for power. These new rulers of Islam assumed the title of Caliph, meaning successor to the Prophet. The Umayyads, having taken over Syria also, now decided to move the seat of government from Muhammad's capital, Medina, to Damascus, Syria. The Umayyad family had served the Romans as auxiliaries, and they had been Hellenized to a considerable extent. Men of science were now brought to Damascus, and an astronomical observatory was set up there around 700. While science dozed in Western Europe, followers of Islam had already begun carving out an empire that stretched from Spain in the west, all along the north of Africa, through Arabia and Persia, and on to China's western border. All of this was accomplished between 634 and 750 A.D. The relatively Hellenized period ended in 749 when the Umayyads were defeated in bloody combat by the Abbasids, a competing Arab family. The Abbasids were considerably more religious than the Umayyads, and they were influenced more by Persia than by the West. The Umayyads, now eclipsed by the Abbasids in the Eastern Caliphate, moved far to the west. One member of the defeated Damascus Caliphate established the independent kingdom of Andalusia in Spain in 755. Back in Syria, the Abbasids soon moved the center of Islamic government from Damascus to Baghdad. The neighboring Persians in the 3rd century had already established a center of ancient sciences modeled on the Alexandrian Museum. Following this example, the second Abbasid caliph, al-Mansur, now set up his own school of science at Baghdad. In 773, the school invited an Indian astronomer to come there to translate into Arabic various Hindu works on astronomy and medicine. These Persian and Indian influences laid the foundation for Islamic astronomy during the Middle Ages, as the Iranian historian of science Sayyid Hossein Nasr has indicated.
The first astronomers in Islam, who flourished during the second half of the 8th century in Baghdad, based their astronomical works essentially on Persian and Indian astronomical tables. The most important astronomical work that has survived from pre-Islamic Persian was the Zij-Shahi or Zij-Shahriyari, the Tables of the King. It was composed around AD 555, based to a large extent on the astronomical theories and practices of the Indians.
It appears that ancient Greek and Babylonian science had been known in India for some time, but it's not easy to tell how and when the knowledge first came there. Few reliable written records have survived from the period before the Muslims invaded India, beginning in 664. India undoubtedly had acquired some very old astronomical knowledge when Alexander invaded in the 4th century BC, but scientific contact between Greece and India apparently ceased no later than about 100 AD. Hindu astronomers knew about Hipparchus, who lived from 190 to 120 BC, but they did not know of Claudius Ptolemy, who lived from 85 to 165 AD. Our modern number system, which we call the Arabic system, was actually adopted from India by the Arabs in the 9th century AD. Clear reference to Hindu numbers outside India is documentable as early as 662 AD, well before their acceptance among the Arabs. In that year, Severus Sebokht, a Christian bishop from the convent of Kaneshra along the Euphrates, mentioned Indian mathematics when he compared the state of knowledge in the West and in the East.
I will omit all discussion of the sciences of the Hindus, their valuable method of calculation, and their computing, which surpasses all description. I wish only to say that this computation is done by means of 9 signs.
India had more closely followed the Babylonian algebraic tradition than the Greek geometric tradition. By about 500 AD, a pair of prominent Indian mathematicians known as the Aryabhatas had made progress in solving quadratic equations, that is, equations of the modern form ax squared plus bx plus c equals 0. They initiated the study of the subject that later became known as trigonometry by introducing what we call the sine of an angle. In about 628, the Indian mathematician Brahmagupta began using algebra to study problems in astronomy. While it's not certain when the concept of zero was first introduced, it was definitely before 876 AD. We have written evidence that it was used in India by that time. The Indian mathematician Mahavira wrote about arithmetic operations at about this time, and he discussed the use of zero. Notably, Mahavira argued that division by zero should always yield zero as a result. It was not until the 12th century that Bhaskara, another Indian mathematician, showed that a more reasonable result of dividing by zero would be infinity, not zero. Not until modern times was it understood that the best analysis leaves division by zero undefined. At any rate, the extraordinarily fruitful Arab-Indian connection began in earnest no later than 773, and events thereafter moved rather quickly. Instruments like the astrolabe were used more frequently in order to carefully measure the altitudes, positions, and movements of heavenly bodies. Translation of Indian classics in Arabia began to be complemented by original observation of the heavens by Arab astronomers, as Sayyid Hossein Nasr points out.
A year or two later, the Zij, astronomical tables of Al-Fazari appeared, based on the Siddhanta of Brahmagupta. Al-Fazari also composed several astronomical poems and was the first person in Islam to make an astrolabe, which later became the characteristic instrument of Islamic astronomy. His major work, which became known as the Great Siddhanta, remained the sole basis of astronomical science until the 9th century.
The Islamic conquests of Asia in the 7th and 8th centuries also brought knowledge from China. Paper had been invented in China by Hua Lun in about 105 A.D., and in 704 Islamic forces captured some Chinese papermakers at the Battle of Samarkand in modern Uzbekistan. By 751, the first Islamic paper mill was established at Samarkand, with another one at Baghdad by 793. Egypt did not have a working mill until around 900, and Europe didn't receive the technology until the 12th century. The third Abbasid Caliph, the immediate successor to Al-Mansur at the end of the 8th century, directed that original Greek works be collected in Baghdad. The 7th Caliph, Al-Mamun, raised the intellectual commitment of the Eastern Caliphate when, in 830, he founded a House of Wisdom to translate these Greek works. The chief translator, Hunayn ibn Ishaq, known in the West as Ioannicius, gathered a staff of about 90 pupils. Within a few years, they had translated the medical works of Galen, Hippocrates, and Dioscorides, along with the astronomical works of Ptolemy and the mathematical works of Euclid. But Hunayn ibn Ishaq was more than just a translator. He also was one of the most important physicians of the era. His own textbook, the Isagogy, revived the Galenic tradition in medicine. It was used as a standard Islamic medical text for the next 2 centuries. In the Galenic tradition, much depended upon fine distinctions, divisions, and subdivisions among both theoretical and practical aspects of medicine. Theoretical medicine was divided into 3 parts, and one of those divisions made distinctions between elements, qualities, humors, energies, spirits, and so on. The elements, for example, were the usual 4 Aristotelian elements: fire, air, water, and earth. Fire was conceived to represent the hot and dry principles, air was hot and moist, water represented cold and moist principles, and earth was cold and dry. The general outlook of this Galenic approach is seen in Ishaq's remarks on the difference between male and female.
The male differs from the female in that he is hotter and more dry. She, on the contrary, is colder and more moist.
In addition to setting up the House of Wisdom, Al-Mamun also established an observatory at Baghdad in 829. Here the astronomer Al-Battani took various measurements supporting the Ptolemaic, or geocentric, theory of the heavens. Also in the 9th century, the Sufi sect of Islam was born. A radical sect of Sufis, the Karmati, taught that all men are equal. They supported science by founding schools, writing grand encyclopedias, and vigorously promoting artisan guilds. In many major Islamic cities, the Karmati established what they called schools of pure brethren. These schools were dedicated to promoting Karmati ideas and projects. One such school at Basra, in what is now Iraq, seems to have been responsible for the main body of work in Islamic alchemy. The historian Stephen Mason has described how the Islamic alchemists saw a new relationship between mystery and reason.
The Brethren of Purity were opposed to the deductive, geometrical kind of reasoning which the orthodox Muslim scholars had inherited from the Greeks. They exalted mystery above reason, and they held that mysteries could be explored empirically. The conception that man is a microcosm of the whole world made the basis of their world system. They found analogies and correspondences between all aspects of the anatomy and physiology of man, and the structure and workings of the world, which were then known. In the specific field of chemistry, they divided natural substances into two main classes, bodies and spirits, by analogy with the view that man was made up of a body and soul. Spirits were volatile substances, bodies were the substances which were non-volatile. They formulated the doctrine that all things, and in particular the metals, were formed by the interaction of the principles of mercury and sulfur. The principle of sulfur was the active, male, and fiery essence. The principle of mercury was the receptive, female, liquid essence.
As in the Alexandrian period, Islamic alchemy could never be entirely separated from what we would now call practical chemistry. The Islamic alchemists used a balance scale to study chemical operations quantitatively. They learned of many chemicals, like mineral acids and saltpeter, which had been unknown to their Hellenic predecessors. Of the 52 treatises in the encyclopedia written by the Brethren of Purity, 17 are devoted to technical scientific matters, while the rest focus more generally on alchemy. But this entire work was later declared heretical to the Islamic religion, and it was burned by the Orthodox Sunni sect, which controlled the government in Baghdad. The Brethren of Purity were entirely suppressed in the 11th century. Abu Ali al-Hasan ibn al-Haytham, known in Europe as Al-Hazen, is often regarded as the greatest physical theorist ever produced by Islam. He was born in Basra and lived from 965 to 1038. One of his greatest achievements was a theory of vision. Euclid, Ptolemy, and other ancient authorities had suggested that human eyes send out rays of light in order to view things, but Ibn al-Haytham disagreed. He suggested that rays of light go the other way, from object to eye, spreading out in a spherical pattern from the source. He also profitably studied magnifying lenses and refraction, improving considerably upon what was known at the time. Ibn al-Haytham's achievements in theoretical optics would not be surpassed until Isaac Newton's dramatic advances more than 600 years later. Abu Ali al-Husayn ibn Abdallah ibn Sina, later known in Western Europe as Avicenna, was a contemporary of Ibn al-Haytham's. He was the most important original philosophical thinker to be produced during the great period of Islamic intellectual glory, between 700 and 1200. Ibn Sina's work was influenced in various ways by Aristotle, Plato, Galen, the Stoics, and Neoplatonism, but his overall philosophical system must finally be attributed to him alone. His metaphysics rested on the idea that the world emanates from necessary existence, which we may understand as God. Both in the later Islamic world and in medieval Western Europe, his influence was considerable. Thomas Aquinas, one of the great figures of Christian thought, was influenced powerfully, even where he disagreed, by the work of Ibn Sina. In many ways, the Dark Ages were at their worst in the parts of Europe far removed from the Mediterranean Sea, far from where science had been born. Near the Mediterranean, the secular schools of Italy probably maintained at least some continuous contact with the classical tradition during the whole period, but not in the north. And in the early Middle Ages, the general intellectual culture throughout Europe was not impressive, as historian Edward MacNaull Burns has pointed out.
Superstition and credulity frequently characterize the work even of many of the outstanding writers. A fondness for compilation rather than for original achievement. Few men any longer had much interest in philosophy or science, except insofar as those subjects could be made to serve religious purposes. Such an attitude naturally led to mystical interpretations of knowledge and to the acceptance of fables as fact when they appeared to be freighted with symbolic significance for the sphere of religion. In spite of all this, the mind of the times was not hopelessly submerged in darkness. The light of antique learning was never entirely extinguished. Even some of the most pious of church fathers recognized the value of classical literature. Moreover, there were a few men in the period who, if not creative geniuses, at least had abilities of scholarship which would not have been rated inferior in the best days of Greece.
Anicius Manlius Severinus Boethius, a Roman philosopher and statesman in the late 5th and early 6th centuries, had translated or paraphrased into Latin many Greek works, including many important works by Aristotle. These books were thus available throughout the Middle Ages for those who took the trouble to seek them out. Yet Boethius's translations were but a small part of a much larger project that he had undertaken and never finished, because he was executed for treason at the order of Theodoric the Ostrogoth in 524. Theodoric had seized power throughout the Italian peninsula in 493, and he had chosen to rule through the established bureaucratic mechanisms. At the end of his life, he increasingly believed that the Roman aristocracy was plotting against him, in conspiracy with his own subordinates. Boethius was executed for reasons related to Theodoric's fear of conspiracy, and apparently unrelated to Boethius's scholarly activities. If it weren't for Theodoric's displeasure and Boethius's execution, subsequent Western history might have been very different. Boethius had planned in the early 6th century to translate all the works of Plato and Aristotle in order to make them available in Rome. The philosophical historian Hermann Shapiro wrote,
Had Boethius managed to accomplish either more or less of the gigantic task that he had undertaken, it is most probable that subsequent intellectual history would have been profoundly altered. As it was, he transmitted to the early Middle Ages the greatest part of the knowledge of Aristotle then available. His application of the Aristotelian philosophical categories to theology instituted scholastic theological science, while his use and definition of philosophical terms was to serve centuries of philosophers and theologians. Finally, we may note that it was Boethius who bequeathed to the medievals what was to become their most characteristic form of philosophical composition, the commentary.
Boethius also described the relation between mathematics and nature, articulating a view that owed a great deal to the Pythagorean number worship in pre-Socratic Greece. Here, for example, is what he says about the nature of numbers in his work entitled Introduction to Arithmetic.
All things constructed from the first nature of things seem to have been formed after the manner of numbers. Indeed, this was the principal exemplar in the mind of the Creator, from which came the multitude of the four changing elements, the alterations in times, the motions of the stars, and the revolution of the sky.
There's no doubt that Boethius's work was particularly important for the subsequent development of science. Historian Edward Grant has put the matter this way.
From the 6th to the 12th century, when Greek geometry had almost vanished and science was at its lowest ebb, Boethius's arithmetic, for all its faults, preserved the ideal of a theoretical science. Not until the 13th century, when Jordanus de Nemours' arithmetic appeared in 10 books, do we have a theoretical arithmetic on the Euclidean model, complete with proofs.
Meanwhile, Western Europe was falling apart. Tribes overran the remnants of the Western Roman Empire. The Angles and Saxons took England, the Franks conquered France, the Vandals seized North Africa, and the Ostrogoths held Italy. Later, after Arab Muslims conquered Arabia in the 7th century, they swept into northern Africa. And there the Muslims converted the native Berbers, or Moors as they've also been called, from Christianity to Islam. With fervent Berber converts as their main troops, Islamic armies crossed into Europe and took Gibraltar and Spain. They were halted by the armies of Charles Martel in France. Charles the Great, or Charlemagne, the Christian leader of the Franks, revived an empire in northern Europe during the late 8th century. Pope Leo III now turned to Charlemagne to protect unstable Italy. Charlemagne ratified the Pope's rule of the Papal States around Rome, and in the year 800, on Christmas Day, the Pope crowned Charlemagne Holy Roman Emperor in a ceremony at Rome. Divisions between the Eastern and Western churches, long the source of uneasy relations, began to deepen in the remainder of the 9th and 10th centuries, and the split became more or less official by the middle of the 11th. The remains of classical civilization were variously preserved at Rome and elsewhere on the Italian peninsula. St. Benedict founded a monastery between Rome and Naples. Benedictine abbeys soon spread throughout Europe. These were among the few institutions to preserve learning in a world of conquest and decay. But after the Roman Empire was divided between East and West, the Eastern, or Byzantine Empire, clung much more closely to the remnants of civilization than did the Western territories. As historian David Lindbergh explains, this had an important impact on the way religious differences were understood and handled.
In the East, the assimilation of the Hellenistic heritage was more thorough, and differences between Christians and pagans assumed the character of a genuine philosophical dialogue on common problems. In the West, Christianity was less concerned with establishing a theology than it was in gaining spiritual control over men. Its primary questions were those of conduct, discipline, and ethics.
Ireland was a bright spot in the otherwise dark picture of Northern European learning. Education in Ireland appears to have been vastly superior to the teaching available on the continent, and during this period, European knowledge of ancient Greek seems to have been limited almost exclusively to Irish monks. Irish education produced, in the 9th century, a brilliant philosopher of nature, the theologian and metaphysician John Scotus Erigena. Ireland was now in the western part of the Carolingian Empire. The word Carolingian derives from the Latin name Carolus, which is translated in English as Charles. Thus, Carolingian describes the empire built by Charles the Great, known also as Carolus Magnus, or Charlemagne. Charlemagne died in 814, and his empire was divided into 3 parts at Verdun in 843. The king of the western region was Charles the Bald, grandson of Charlemagne. He worked to continue the intellectual renaissance begun by his grandfather. Charles followed the tradition by scouring all of Europe for its most distinguished scholars, and he invited Erigena to take charge of the court school at Paris. Erigena became the most important original thinker to arise in Latin Christendom between the 5th and 11th centuries. His metaphysical doctrines were extremely influential, even while being condemned by ecclesiastical authorities. Erigena worked mainly to reconcile revealed scripture with reason. He understood himself to be defending revealed scripture against charges that Christian doctrine was irrational. Unfortunately for Erigena, church authority did not see things quite his way. In 855, the Synod of Valence condemned 19 of his theses, declaring them heretical. 2 conflicting stories about how Erigena died, both possibly apocryphal, managed to evoke how his work influenced his own time. One story says that after Erigena became abbot of Athelney, he was murdered by the monks. Another story suggests that after he was called to England to teach during the reign of Alfred the Great, a group of students who didn't like his lectures stabbed him to death with their pens. Erigena addressed mostly theological questions in his work entitled The Division of Nature, but he also included several theses of a more physical kind. For one thing, Erigena advanced a theory of gravity, suggesting that heaviness and lightness vary with distance from the earth. He also offered a theory about the movement of the heavenly bodies. He accepted the prevailing view that the sun moves around the earth, but he suggested that Venus, Mercury, Mars, and Jupiter orbit the sun. Erigena's reasoning was interesting.
As for the planets which revolve about the sun, they assume different colors according to the quality of the regions which they cross. I am referring to Jupiter and Mars, Venus and Mercury, which ceaselessly circle the sun. When the planets are above the sun, they show us their clear face, but they look red whenever they are below it.
This suggestion about the planetary movements was possibly inspired by a misreading of other sources, yet it anticipated the 16th century theory of Tycho Brahe. Brahe would later say that all planets other than the Earth orbit the Sun, while the Sun itself moves in a circular orbit around the Earth. But Erigena's theory appears to have developed in large measure out of his theology, and certainly not out of the detailed observation that supported Brahe's later theory. Erigena in the 9th century said that Venus, Mercury, Mars, and Jupiter all orbit the Sun. Some astronomers had long before accepted the slightly less daring view that only Mercury and Venus orbit the Sun. The two-planet orbit of the Sun was first suggested by Heraclides of Pontus in the 4th century B.C. This view had been passed on to the Middle Ages by Chalcidius in his 4th century translation and commentary on Plato's work, the Timaeus. Here is Chalcidius's rather fuzzy description of the Heraclitean picture, in which he refers to the moon as Lucifer.
Heraclides Ponticus, when describing the circle of Lucifer as well as that of the sun, and giving the two circles one point and one middle, showed how Lucifer is sometimes above, sometimes below the sun. For he says that the position of the sun, the moon, Lucifer, and all the planets, wherever they are, is defined by one line passing from the center of the earth to that of the particular heavenly body.
Chalcidius's work provided the primary basis for medieval knowledge of Plato. His book presented the most systematic approach to natural philosophy that could be had until further translations of the classics became available in the 12th century. Other 4th and 5th century commenters like Macrobius and Marcianus Capella read this work by Chalcidius and passed along the reference to Heraclides in their own work, with varying degrees of clarity. Perhaps the clearest portrayal of the Heraclitean view was offered by Capella, who lived in Carthage and expressed the idea as if he'd thought of it.
Although Venus and Mercury are seen to rise and set daily, their orbits do not encircle the earth at all, but circle round the sun in the center of their circles, so that they are sometimes carried above it, at other times below it, and nearer to the earth.
When Nicolaus Copernicus in the 16th century offered his theory that even the earth was a planet, and that it too circles the sun, he insisted that his own view was only an extension of what he called the ingenious view held by Marcianus Capella. Finally, Erigena in the 9th century reported on and explained the ancient work of Eratosthenes concerning the circumference of the earth. But in trying to calculate the distance from the earth to the moon, Erigena erroneously thought that the right way to figure the diameter of the earth was to take half the earth's circumference. For the latter number, he used Eratosthenes' ancient estimate of about 24,000 miles, which is close to the modern figure. Erigena then concluded that the distance to the moon was equal to the Earth's diameter, a distance only about 1/30th as far as the actual distance. In matters concerning scientific questions, Erigena's original contributions were vastly less significant than the ancient material he passed along. His contribution to 9th century intellectual life shines out mostly because of the darkness of the age. At the close of the Dark Ages and the beginning of the medieval era in the 11th century, a few brave souls began hesitantly to venture out of the darkness on the European continent. They sought to learn about the larger world and about what glories of classical European thought were preserved in other lands. A 20th century historian has characterized these medieval scientists rather compellingly.
These men were daring, original, inventive, skeptical of traditional authorities, although sometimes overly impressed by new ones, and above all, steadfastly determined to discover purely rational explanations of natural phenomena. These explanations were usually painfully ad hoc, indicating the lack of a coherent, self-consistent worldview or a carefully worked-out method of investigation. Nevertheless, the conviction of these scientists that nature operated in a uniform manner, according to rational laws which man had the power to discover, their intense interest in the natural world for its own sake, their habits of precise observation of natural phenomena, and the high value they placed on man as a rational being, portended a new age in the history of scientific thought.
Adelard of Bath, an Englishman, was one such intellectual explorer. Born in about 1080, Adelard spent an unusually large part of his life traveling to Italy, Greece, Syria, Palestine, and Spain. He said he did it all for the sake of knowledge. In his many travels, Adelard was powerfully impressed by the way knowledge was pursued differently in foreign lands as compared to Europe. He was especially in awe of Arab wisdom. Upon returning from a trip relatively early in his career, he explained to a curious nephew that authority had retarded the wisdom of the European people.
"It is difficult for me to talk with you, for I have learned one thing under the guidance of reason from Arabic teachers, but you, captivated by a show of authority, are led around by a halter. For what should we call authority but a halter? Indeed, just as brute animals are led about by a halter wherever you please, and are not told where or why, but see the rope by which they are held, and follow it alone, thus the authority of writers leads many of you, caught and bound by animal-like credulity, into danger. Whence some men, usurping the name of authority for themselves, have employed great license in writing, to such an extent that they do not hesitate to present the false as true to such animal-like men. For why not fill up sheets of paper, and why not write on the back too, when you usually have such readers today, who require no rational explanation, and put their trust only in the ancient name of a title?"
Adelard insisted that reason is given to everyone, not just the authorities, though some people act as though they don't know it.
For they do not understand that reason has been given to each person, so that he might discern the true from the false, using reason as the chief judge. For if reason were not the universal judge, it would have been given to each of us in vain. It would be sufficient that it were given to one, or a few at most, and the rest would be content with their authority and decisions. Further, those very people who are called authorities only secured the trust of their successors because they followed reason. And whoever is ignorant of reason, or ignores it, is deservedly considered to be blind.
Adelard now sums up the relationship between authority and reason.
I will cut short this discussion of the fact that in my judgment authority should be avoided, but I do assert this, that first we ought to seek the reason for anything, and then, if we find an authority, it may be added. Authority alone cannot make a philosopher believe anything, nor should it be adduced for this purpose.
The Dark Ages had suppressed reason among Europeans for half a millennium. Now, after Adelard's death in the 12th century, it would be another 5 centuries before enlightenment fully returned to that continent. Even before the Carolingian Renaissance of the 9th century, the disintegrating Western Roman Empire had been influenced by external forces, some of them barbaric. Progress in understanding nature owed more to craftsmen or tradesmen than it did to scholars. And these changes, as we'll see, were vitally important in setting the stage for later developments in science, as historian Stephen Mason observes.
During those centuries appeared a number of fundamental technical innovations which provided the basis of a way of life materially superior to that of classical antiquity for the majority of men. The Teutonic barbarians who invaded the disintegrating Roman Empire brought with them numerous small things to which we are accustomed: the wearing of trousers instead of the toga, the use of butter instead of olive oil, improved methods of felt making, the ski, and the making of barrels and tubs. More important were the introduction by the barbarians of the cultivation of rye, oats, wheat, and hops, the use of the stirrup for riding horses, and, above all, the heavy wheeled plough that provided the means for the development of the three-field system on which the life of the medieval manor was based.
The heavy-wheeled plough had been used by the Teutons since about 100 BC, but it was still a novelty in 8th century Roman lands. This plough dug deeper and more regular furrows, and by 765 AD, its use led to the development of the three-field or three-course agricultural system. Now the land could be harvested 2 years out of every 3 years instead of only one harvest every 2 years. As Mason emphasizes, this yielded a dramatic improvement in the productivity of the land.
The chief novelty of the three-course system was the sowing of crops in the spring in addition to the traditional winter sowings. In a typical cycle, the first year would be devoted to a winter sowing of wheat or rye, the second to a spring sowing of oats, barley, beans, or peas, while the land would lie fallow in the third. Thus, given the same productivity per unit area of land, the northern three-course system would produce a third as much again as the southern two-course system.
In the older system, it had been difficult or impossible to grow enough grain to feed horses. Oxen were the beasts of burden, fed with hay. The three-course system now made surplus grain available for the horses. Horse collars were introduced, probably from Asia, by the 9th and 10th centuries. The iron horseshoe and the tandem harness were introduced. All of these developments together were now responsible for multiplying the plow's effective pulling power by 3 or 4 times. Stephen Mason tells us that another device, the water wheel, became increasingly important in the Dark Ages.
Human or animal-driven querns were generally used for grinding corn in antiquity, mills becoming common only during the Dark Ages. The Domesday Book of 1086 lists some 5,000 mills in England at that time, indicating that there was about 1 mill to every 400 of the population. During the next century, windmills appeared. The first mentioned was a Normandy mill of 1180, which possessed a horizontal driving shaft and vertical sails, so that it was probably an invention independent of the 10th century Oriental windmills, which had vertical driving shafts.
All these developments eased the back-breaking labor that workers had long endured. Some of the hardest work could now be done with machinery and animals, and it could be done much faster. More food and goods were now produced, and more energy and attention were available for pursuits beyond basic survival. As production grew, so did trade. Market towns became larger and more important. The new wealth began to make grand projects possible in the 11th century. Soon there were the great European cathedrals and the first European universities. There also were the Holy Crusades, a lengthy series of medieval adventures designed to conquer Jerusalem in the name of Christianity and to enrich European coffers. Stephen Mason tells of the scope of this surge of activity.
The craftsmen and the students of the big cities were fed and supported with the food surpluses. So too were the cathedral builders. The 80 cathedrals built by the French between 1170 and 1270 cost the modern equivalent of $1,000 million in labor and materials.
Commerce continued to expand, especially in northern Europe. This area had been less controlled by the Romans before the fall of the empire. It had benefited less from imperial civilization. So the north had plumbed the intellectual depths of the Dark Ages much more deeply than the southern regions had. But the absence of a strong central government also had economic benefits, and booming trade led, by 1241, to the formal establishment of the Hanseatic League, a mercantile organization of mainly German towns. A Hansa originally was a company of merchants who traded with people in foreign lands. The German peoples began to establish settlements and towns farther and farther to the east, especially along the Baltic coast, and their local merchant guilds and town associations kept in contact through leagues. Eventually, the Hanseatic League came to include 172 cities and towns across Europe. Hamburg, Lübeck, Cologne, Breslau, and Danzig were leading trade centers, with international sites in what are now the nations of England, Belgium, Sweden, Norway, and Russia. North European trade, especially around the Baltic Sea and the North Sea, began to rival the volume of trade in the Mediterranean. Civilization began gradually shifting from the Mideast and from southern Europe more toward northern Europe. Discoveries now made navigation more efficient and increased sailing distances. The fore and aft rig enabled ships to sail into the wind. Though the rig had been known in the eastern Mediterranean before the 7th century, it was widely used in the north only in the 13th century. These ships could now make ocean-going voyages, where they navigated by the stars. Fogs and cloudy skies were more common in northern waters than in the Mediterranean, so navigating by the stars was not always so easy in the north. The compass, which appeared in Europe in the 13th century, was thus developed and improved more rapidly in the north than in the south. The 15th century compasses made in Flanders even compensated for the fact that magnetic north, the direction in which the needle of a compass tends naturally to point, differs from true north. Compasses made in Genoa made no such compensation. These developments paved the way for the great voyages of exploration in the 15th and 16th centuries. They also fueled the growing interest in astronomy, which improved both navigation and map-making. Paper-making, which had been brought from China by Arab armies in the 8th century, became well established in Spain by 1150, in France by 1189, in Italy by 1276, and in Nuremberg, Germany by 1391. England's first paper mill was established in 1494. Printing also originated in China. It seems to have been brought to Europe by Mongol invaders in the 13th century. Printed playing cards, long known in China, began to appear in Europe shortly after the Mongol invasions. Before these invasions, the monks at Engelberg in what is now Switzerland had cut wood blocks for crude printing. These blocks had been used to imprint the large and intricate capital letters that begin paragraphs in medieval manuscript work. But after the Mongols came in 1289, block printing flourished at Ravenna, Italy. Soon the use of movable and metal type became widespread. Finally, between 1436 and 1450, Johann Gutenberg perfected the method of printing that became standard in Europe, setting the stage for intellectual revolution in Europe and then throughout the world. As printed books became more available, collectors began to seek them for their personal libraries, but it's not easy to measure the overall effect of the printing press on these library collections, as the historian Pearl Kibre notes.
The contribution of the printing press to the growth of these libraries is difficult to evaluate, since printed books did not at first find a ready acceptance among the wealthy bibliophiles, who preferred the more costly and more finely wrought hand copies. Yet the humanists and other scholars, whose chief interest was in the content rather than in the externals of the books, welcomed the products of the presses.
Gunpowder, another Chinese discovery, had been developed as early as the 3rd century A.D., when experimental alchemists had mixed sulfur and saltpeter and exposed it to high temperatures. Fireworks were mentioned in 7th century texts in China, and in 969 a rocket apparently was developed. These rockets replaced the older fire arrows that hurled burning pitch on the end of a common arrow. In 1231, the Tatar armies used an iron container filled with gunpowder, ignited with a fuse, and hurled from a catapult against the Mongols. This appears to have been the first use of the grenade. By 1259, a firearm that projected bullets was used by China's Sung armies, who pushed back the Tatars with weapons made out of bamboo tubes. In 1233, a Mongol general named Subutai captured a Chinese ammunition works. Within a few years, the same general led the Mongol invasions of Europe. Gunpowder probably was introduced to Europe in these invasions. The first European mention of it appears in a letter written by the English philosopher and scientist Roger Bacon in 1249. Bacon was long thought to have independently invented gunpowder, but this now seems improbable. As Stephen Mason observes, both printing and gunpowder had an enormous effect on Europe.
Printing and firearms at the end of the Middle Ages had effects similar to the inventions of the alphabet and iron-making at the end of the Bronze Age. Printing, like the alphabet before it, served to increase the literacy of mankind, and made the accumulated records of human civilization more available. It made possible the rise of the vernacular and craft literatures, the artisan for the first time in history recording the experience and values of his tradition. Gunpowder and firearms ended the days of the armored knight and his fortified castle, just as iron weapons had eliminated the Bronze Age knights with their chariots and bronze rapiers. Military power was concentrated in the hands of the prince, who commanded the control of gunpowder making and cannon casting. Thus, the development of firearms gave an impetus to the rise of the absolute monarchies of the 16th and 17th centuries.
Yet even as the Mongol armies left behind their weapons and their playing cards, they learned a few things in the West that were still unknown in the East. The returning Mongols brought knowledge of distilled alcoholic liquors and eyeglasses for the first time to China. Which side got the better of this exchange is anyone's guess. While firearms revolutionized warfare and printing revolutionized schooling, water power was profoundly changing the manufacturing arts. In the textile trade, water-driven trip hammers were being used by the 12th century in a process called fulling. This process helped to increase the density and durability of cloth products, a task formerly achieved by hand. By the 13th century, sawmills and blacksmith bellows were powered by water, followed by water-powered grindstones and pumps for draining mines. Cast iron, first developed in Europe in the 13th century, was by the 15th century made in blast furnaces with water-powered bellows. These blasted air into the furnace to raise the temperature of the fire. Expanding production and trade led to new techniques, discoveries, crafts, and skills. Artisans, engineers, instrument makers, smithies, and millwrights each became more specialized. All of this led to the increasing domination by the associations of artisans or merchants called guilds. The rules governing the English Guild merchants of Southampton show how much the associations restricted business transactions in order to benefit their membership.
No one of the city of Southampton shall buy anything to sell again in the same city, unless he is of the guild merchant, or of the franchise. And if any one shall do so, and is convicted of it, all which he has so bought shall be forfeited to the king. And no one shall be quit of custom, unless he proves that he is in the guild, or in the franchise, and this from year to year. And no one shall buy honey, fat, salt herrings, or any kind of oil, or millstones, or fresh hides, or any kind of fresh skins, unless he is a guildsman, nor keep a tavern for wine, nor sell cloth at retail, except in market, or fair days, nor keep grain in his granary beyond 5 quarters, to sell at retail, if he is not a guildsman. And whoever shall do this and be convicted shall forfeit all to the king.
Training came to require such dedication that artisans focused on smaller and smaller ranges of personal skills. Sculptors and artists soon represented crafts on their own, distinct from the crafts of the decorator, the stonemason, and the architect. Each specialty produced ever greater precision, efficiency, and refinement. For example, the mechanical clock was developed during the 13th and 14th centuries. Most mechanical clocks were mounted in large public buildings because of their huge size and great weight. These were prominent examples of human artifice in the 14th century. As we've seen, artifice was believed to be non-natural or preternatural, so many people saw clocks as prime examples of magic. The historian Bert Hansen says that mechanical clocks also had a special quality that impressed observers.
People saw mechanical clocks as magic, not simply because they were complex, but because as self-moving and self-regulating devices, they had a kind of creature-like autonomy, lacking in ordinary machines of the day such as water wheels, windmills, or pulleys.
As craftsmanship improved, mechanical clocks became smaller, more delicate, and more common. Pocket watches were made in Nuremberg by the 16th century, an early example of miniaturization that would be seen again in the computer revolution of the 20th century. And as people became more familiar with the new clocks, they seemed increasingly more natural. The processes for building them gradually became ever less magical. It was a similar story for the many contrivances and processes that continued to arise as the medieval period progressed. The Middle Ages brought improvements in architecture, shipbuilding, the design of machinery, and in agriculture. All of these developments led to greater demands upon craftsmen. The more literate craftsmen recorded what they learned, both from their teachers and from experience. This growing literary tradition among the crafts began to make tentative contact with a scholarly tradition still confined largely to monasteries. Monks had long sought wisdom in the books of speculative philosophers and theoretical theologians, rather than in the world of production and trade. Stephen Mason compares these traditions.
From as far back as 1250, we have the notebooks of the master mason Villard de Honnecourt, who travelled widely, going to Hungary to rebuild churches after the Mongol invasions, and recording various things he had seen. His drawings of living beings are realistic and based on observation. He notes specifically that his lion is drawn from the life, though it was a heraldic-looking creature. The scholarly drawings of animals and plants, on the other hand, were copied from earlier manuscripts, so that there was a rapid generation of realism, biological illustrations becoming formal and conventionalized. A plant which appeared as a strawberry in a French herbal about 550 had come to look rather like a blackberry in a Rhenish herbal of 1050, after numerous copyings without reference to the plant itself.
The concern of craftsmen for empirical accuracy was increasingly apparent by the dawn of the 15th century. This empiricism was vitally important to the development of modern science. It was responsible for what we now know as the experimental method. The Italian painter Cennino Cennini, working in Florence in about 1400, wrote a book on painting, not in Latin, but in vernacular language. Dedicated to apprentices of the craft, the book described the techniques for making pigments and carefully noted Cennini's experiments and their results. Matthias Roricher, a Gothic master builder, wrote a book whose aim was, in his words,
to better wheresoever something is to be bettered, and to amend and explain the arts.
As craftsmen refined their specialties, the demand for information increased. Architects who tackled ever more complicated questions of design needed to understand more and more about materials, about their weight-bearing properties and how these properties affected the design of load-bearing supports. Artists also sought to explore their subjects in ever greater detail. They needed to better understand light, pigments, anatomy, and much more. These developments paved the way for the great artist-engineers of the Renaissance, men like Sandro Botticelli, Albrecht Dürer, Michelangelo Buonarroti, and Leonardo da Vinci. Their studies, their notes, and their finished work emphasized the need for careful observations and experiments. Indeed, these Renaissance men became quite reflective about how one can learn about nature. Leonardo da Vinci offered a fine example in the way he self-consciously examined his own method.
In dealing with a scientific problem, I first arrange several experiments, since my purpose is to determine the problem in accordance with experience, and then to show why the bodies are compelled so to act. That is the method which must be followed in all researches upon the phenomena of nature. We must consult experience in the variety of cases and circumstances until we can draw from them a general rule that is contained in them. And for what purposes are these rules good? They lead us to further investigations of nature and to creations of art. They prevent us from deceiving ourselves or others by promising results to ourselves which are not to be obtained.
The medieval craft tradition, more than anything else, helped develop the experimental outlook that characterizes modern science. Yet, modern science involves more abstract theory than the craftsmen of the Renaissance ever envisioned. For the theoretical roots of science, we must explore the monasteries, the old universities, and the houses where the medieval nobility lived. In the Middle Ages, only a few wanderers like Adelard of Bath had wandered around Europe in search of knowledge, but those who gained great knowledge were regarded as sorcerers or worse. A historian tells us of one example.
In the 10th century, Gerbert, a young monk from the Burgundian monastery of Aurillac, went off to northern Spain to acquire some mathematical skills unobtainable at home, then traveled to Rome and to Reims to learn logic, also unobtainable at home. After a long career as a scholar and teacher, and tutor to a future king of France and to a future emperor, Gerbert was made pope in the year 999. Gerbert's career was productive, and he was in many ways a remarkable individual, yet Gerbert's learning was regarded by many as being so strange that it must have had diabolical origins, and the unsavory reputation of being a magician and a sorcerer hung about his name for centuries.
Meanwhile, there were important scientific developments in the Muslim world. The Abbasid family had wrested power in the Eastern Caliphate in 749, and a member of the defeated Umayyad family had moved west to Spain. There he established the kingdom of Andalusia. By the 10th century, the descendants of this branch of the Umayyads referred to themselves as the Caliphs of Cordoba. The Caliphs' renewed understanding of themselves as successors to the Prophet produced a similarly renewed commitment to learning. In 970, the Umayyads set up a library and scientific academy in Cordoba, soon followed by a second center of learning in Toledo. One of the early scholars at these academies was a physician named Abul Qasim al-Zahrawi, known in most of Europe as Abul Qasis. His important medical handbook discussed previously neglected surgical techniques. Astronomy also was pursued in both Cordoba and Toledo under scholars like al-Zarqali, who drew up new astronomical tables in 1080. Al-Zarqali improved upon Ptolemy's cosmology by suggesting that Mercury's movement in the night sky could be more accurately modeled as an elliptical motion, rather than the collection of perfect circles previously used to describe it. Ironically, this scientific activity was increasing just as Christians invaded Spain from the north. Toledo fell in 1085. Though Christians won most of the important victories by the early 13th century, pockets of Islamic power would remain in Spain until 1492, when the Spanish King Ferdinand and Queen Isabella finally conquered Granada. In the meantime, control of the Eastern Caliphate at Baghdad had been effectively surrendered to Seljuk Turk mercenaries by 1057, and the Abbasid caliphs of Baghdad maintained only a nominal rule. The Persian poet and mathematician Umar Khayyam, the Islamic scholar most widely known in the West, flourished under the new Seljuk regime. Khayyam was a member of Islam's mystical Sufi sect, and his approach to knowledge illustrates the Sufi belief that those who wish to understand anything must purge themselves of individuality.
The Sufis do not seek knowledge by meditation or discursive thinking, but by purgation of their inner being and the purifying of their dispositions. They cleanse the rational soul of the impurities of nature and bodily form until it becomes pure substance. It then comes face to face with the spiritual world, so that the forms of that world become truly reflected in it without doubt or ambiguity. This is the best of all ways, because none of the perfections of God are kept away from it, and there are no obstacles or veils put before it. Therefore, whatever ignorance comes to man is due to the impurity of his nature. If the veil be lifted and the screen and obstacle removed, the truth of things as they are will become manifest.
Apart from mathematical work in the poetry known as the Rubaiyat, Umar Khayyam is especially noted for designing a highly accurate solar calendar based on Ptolemaic cosmology. Khayyam's calendar was even more accurate than the Gregorian calendar, which was developed much later, in 1585, and is still the basic calendar used today. While Umar Khayyam and some other Islamic scholars stayed in Baghdad during the Seljuk dominance, the center of Eastern science moved to Cairo. Al-Hakim, a caliph of the Fatimid family, had established a house of science in Cairo in 995. There the astronomer Ibn Yunus had prepared in the year 1007 an important new set of astronomical tables, the Hakamite tables, named in honor of the caliph. Ibn Yunus was regarded by some as the most important Muslim astronomer because of his extremely accurate tables. He also was an accomplished mathematician, and Yunus may have been the first scientist to investigate the motion of an oscillating pendulum. Cairo also became a significant center of medical research in the 12th and 13th centuries. Some of Galen's classical ideas were criticized by researchers who had been brought to Cairo from abroad. One of these was the great Jewish philosopher Moses ben Maimonides. He became physician to the Sultan, Saladin, in the second half of the 12th century. Maimonides and his family had fled Spain when he was 13 years old, settling finally near Cairo. As a mature scholar, Maimonides' interests were broad indeed. Among other things, he worked to undermine the Ptolemaic conception of so-called eccentrics and epicycles. He used arguments that became widely influential among 12th century Islamic astronomers in Spain.
As far as the action of ordering the motions and making the course of the stars conform to what is seen is concerned, everything depends on two principles, either that of the epicycles or that of the eccentric spheres, or on both of them. Now, I shall draw your attention to the fact that both those principles are entirely outside the bounds of reasoning and opposed to all that has been made clear in natural science.
For Maimonides, a theory's ability to save the phenomena does not mean that it's a good account of what actually happens in nature. Another researcher, Ibn Nafis, had been brought from Damascus to run the Nasri Hospital in Cairo. He rejected Galen's doctrine that blood passes through the heart's dividing wall, or septum. Ibn Nafis saw that the septum was solid, so it cannot allow blood to pass directly from the right ventricle to the left ventricle. He believed the only alternative was that blood moves through the lungs. Ibn Nafis essentially discovered what's called the lesser circulation of the blood in Cairo in the 13th century. Until recently, this discovery was attributed to the 16th century Spanish physician and theologian Miguel Serveto, known in Latin as Michael Servetus. Serveto actually rediscovered the lesser circulation about 3 centuries after Ibn Nafis. Even after the Seljuk conquest, the Abbasid family formally held the Eastern Caliphate until 1258. But this suddenly ended when Hulagu Khan, the grandson of Genghis Khan, crushed all pretense by sacking Baghdad. The Mongols by now had conquered territories stretching from the Mediterranean to Beijing. They'd also begun setting up their own observatories and centers of learning. Hulagu established such a center in 1261 at Maraga, in what is now Iran, and he encouraged the idea that a library should be built to hold about 400,000 volumes. Historian Sayed Hossein Nasr offers some insight into the historical importance of the Maraga Observatory.
The development of the observatory reached new heights with that at Maraga. It was well equipped with astronomical instruments, including a mural quadrant with a radius of about 430 centimeters, armillary spheres, solstitial armilla, equinoctial armilla, and azimuth rings. But the observatory at Maraga was not just a place for astronomical observation. It was a complex scientific institution in which nearly every branch of science was taught, and where some of the most famous scientists of the medieval period were assembled.
Astronomers like Fu Mengqi from China and Muhi al-Din al-Maghribi from Spain were brought to Maraga from far and wide. A set of improved astronomical tables called the Ilkhanate tables was produced at Maraga in about 1274. The Mongol interest in astronomy continued at least through 1420, when one of the greatest observatories of all time was established at Samarkand. This one was built by Ulugh Beg, who was the grandson of Tamerlane, the bloody conqueror of the East. Ulugh Beg was himself a competent astronomer, and he saw to it that nothing was spared in building his observatory. The Samarkand maps of the stars were more accurate than all others. They were not surpassed until Tycho Brahe began his work in the 16th century. The observatory became a center of scientific interaction. One of the most eminent scholars there, the master mathematician Ghiyath al-Din al-Kashani, described the discussions at Samarkand in a letter to his father.
Shortly after the arrival of the servant here, and in a meeting in which His Majesty took part, this servant was speaking about a few problems on which there was agreement among many prominent sources, but they were nevertheless wrong. My contention reached the ears of all the learned people by word of mouth. They were excited and busy, speaking behind my back. When a person objects to a thing on which so many authorities are in agreement, they declared, he should prove his statement. One day, at a gathering where the majority was present, I spoke on one of these controversial topics which I have thoroughly investigated, and I explained it both in a descriptive way and by geometrical proof in such a manner that it was accepted unanimously. As His Majesty is a scientist himself and well-versed in the subject, and as scientists are present here in large numbers, when a question becomes settled, no one who has previously spoken in another vein can demur, pretending to find faults, so as to make those who are not familiar with the topic believe in him. For the most distinguished scientists are present here.
The Muslim Empire eventually collapsed at the hands of Christians in the West and Mongols in the East. Nevertheless, the scientific contributions made by this culture, the Saracens as they were called in Europe, continued to be felt in the West. The historian Edward MacNaull Burns has summarized their legacy.
In no subject were the Saracens further advanced than in science. In fact, their achievements in this field were the best the world had seen since the end of the Hellenistic civilization. The Saracens were brilliant astronomers, mathematicians, physicists, chemists, and physicians. Despite their reverence for Aristotle, they did not hesitate to criticize his notion of a universe of concentric spheres with the Earth at the center. And they admitted the possibility that the Earth rotates on its axis and revolves around the sun. Their celebrated poet, Omar Khayyam, developed one of the most accurate calendars ever devised by the mind of man. The Saracens were also capable mathematicians and developed algebra and trigonometry considerably beyond the stage they had reached in Hellenistic times. While they did not invent the celebrated Arabic system of numerals, they were nevertheless responsible for adapting it from the Indian system and making it available to the West. Saracenic physicists founded the science of optics and drew a number of significant conclusions regarding the theory of magnifying lenses and the velocity, transmission, and refraction of light. As a result of innumerable experiments by chemists and alchemists alike, various new substances and compounds were discovered, among them carbonate of soda, alum, borax, bichloride of mercury, nitrate of silver, saltpeter, and nitric and sulfuric acids. In addition, Muslim scientists were the first to describe the chemical processes of distillation, filtration, and sublimation.
Even after Toledo fell to Christian crusaders in 1085, Islamic science continued to flourish in Spain. But now there were fewer barriers to stop the communication of these Muslim achievements into northern Europe. By the early 12th century, the Spanish Muslim astronomers began criticizing the Ptolemaic system. Ibn Bijah, known in the West as Avum Pathe, was one of the most important of these critics. Others included Ibn Tufayl, called Abu Bakr in Latin, and the extraordinarily influential Abul Walid Muhammad ibn Rushd, known in Europe as Averroes. All of these scholars were attracted to Aristotle's theories, yet it was Ibn Bijah who first proposed an astronomical system without the elaborate cycles and epicycles suggested by Ptolemy. Ibn Bijah described the variations in planetary orbits by using a system of eccentric circles. His criticisms were elaborated by Ibn Tufayl, that is, Abu Bakr, and improved by al-Bitruji, or Alpetragius. All of these critics said the universe should rotate around a real physical body, not merely an abstract geometric point, as urged by most interpreters of Ptolemy. The contributions of Ibn Bijah and Ibn Tufayl were tremendously important to science, but Ibn Rushd, their younger contemporary, more deeply influenced the philosophical development of the medieval period. Ibn Rushd had been born in about 1126 in a Cordoban family traditionally associated with administering Islamic law. The study of Islamic law amounts to a religious study. Judges had both civil and religious responsibilities. Ibn Rushd's grandfather was the chief judge, or Gadi, of Cordoba. Some traditions suggest that his father also held that position, and Ibn Rushd himself became the chief Gadi of Cordoba in 1171. Ibn Rushd influenced European thought mainly through his commentaries on the work of Aristotle. His interpretations made Aristotle's work seem similar to those of Plato, to a degree beyond what most scholars would now accept. This probably eased the European transition from Platonism to Aristotelianism throughout the 13th to the 17th centuries. Ibn Rushd also wrote an impressive array of scientific, philosophical, and religious works. He wrote commentaries on Galen and Ibn Sina, and a medical encyclopedia entitled the Kulliyat. He appears to have written some works on astronomy, plus various tidbits on divine law, logic, natural philosophy, and medicine. Ibn Rushd's views on religion are well represented in a book entitled The Incoherence of the Incoherence, where he defends the use of natural reason in matters of divine law. Ibn Rushd died in about 1198, just as the greatest period of Arab intellectual development was ending. By this time, an intellectual rebirth was occurring in Western Europe, based on access to ancient Greek knowledge through Islamic research centers in Spain. Scholars there could speak Arabic, Latin, and Greek, and they translated classic works into Latin, the scholarly language of Europe. The 20th century English historian Stephen Mason offers an interesting side note when he says that the translations might have begun earlier.
The revival of Greek knowledge might have come earlier than it did, for Toledo remained a Christian archbishopric throughout the Muslim occupation. Indeed, it is possible that earlier attempts to transmit Greek science to the West were discouraged, as a 9th century Roman ecclesiastic expressed his concern at the fact that Spanish Christians were studying Arabic works.
Sicily, having been under Muslim rule for 130 years, fell to Christian conquerors in 1091. Sicily now became a second contact point with Islamic science, though it was not as important as Toledo. A Scotsman, appropriately named Michael Scott, translated many Arab alchemical texts in the late 12th and early 13th centuries, and he also translated the biological works of Aristotle. The trade route connecting Sicily with North Africa brought yet more ancient works to eager translators. These included mathematical texts, translated by Leonardo of Pisa, and medical materials sent by Constantine the African. A vast array of materials suddenly became available to educated Europeans. Among these works, the Christian translators clearly preferred Roman and Greek authors with familiar names. Many of Aristotle's works now became known for the first time, leading to the Aristotelian movement that replaced Platonism. Europe was now building the foundation for a breakthrough. During the earlier Middle Ages, advanced learning had typically occurred in centers associated with the great cathedrals of Europe. Students had gathered there to apprentice themselves to the masters of their chosen profession. These craft associations of students and masters began by the 11th century to be described interchangeably as guilds and as universities. The official rules of the University of Paris, approved by the papal legate in 1215, show that things by then had become a good deal more formal.
No one shall lecture in the arts at Paris before he is 21 years of age, and he shall have heard lectures for at least 6 years before he begins to lecture, and he shall promise to lecture for at least 2 years, unless a reasonable cause prevents, which he ought to prove publicly or before examiners. He shall not be stained by any infamy, and when he is ready to lecture, he shall be examined according to the form which is contained in the writing of the Lord Bishop of Paris, where is contained the peace confirmed between the Chancellor and scholars by judges delegated by the Pope.
The term university had come to designate student associations of 3 basic types. Institutions such as those at Paris, Oxford, and Cambridge were set up as closed corporations of students and masters, administered by a chancellor. At Bologna and Padua in Italy, the universities were governed by a rector, elected by the students. Finally, some universities were formal state institutions, like those at Naples, Italy, and at Salamanca in Spain. These state schools were founded by the local kings, but with papal recognition. New materials and new attitudes soon led to criticism of Europe's traditional learning methods. This was especially true in Britain, where revolution was in the air. Since 1066, when William the Conqueror had successfully invaded England from Normandy, England's monarchy had been much stronger than before. As a Saxon chronicler indicated at the time, all power appeared for a time to be vested in William, the new ruler from across the Channel.
He caused castles to be built, and oppressed the poor. The king was also of great sternness, and he took from his subjects many marks of gold, and many 100 pounds of silver, and this either with or without right, and with little need. He was given to avarice, and greedily loved gain. He made large forests for the deer, and enacted laws therewith, so that whoever killed a hart or a hind should be blinded. As he forbade killing the deer, so also the boars, and he loves the tall stags, as if he were their father. He also commanded concerning the hares, that they should go free. The rich complained, and the poor murmured, but he was so sturdy that he recked not of them. They must will all that the king willed, if they would live, or would keep their lands, or would hold their possessions, or would be maintained in their rights.
In particular, William reduced the traditional feudal power of the nobility. He ruled until 1087. The middle years of the 12th century provided a brief anarchic interlude in England. After Henry I died in 1135, 5 rival claimants fought for the throne. The power of the nobility again surged. But in 1154, when Henry II became king, he immediately embarked upon a campaign to put the nobility in its place. He destroyed hundreds of castles that had been built without authorization by the crown. He severely curtailed the jurisdiction of the feudal courts. To further undermine local custom, he urged that the national system of justice, which at that time was small, be expanded and developed. And this ultimately came to be recognized as the common law of England. Out of it came the modern institutions of the grand jury and the trial jury. By 1215, times had changed again. Henry's sons and successors, King Richard I and King John, were burdened externally by the Third Crusade. They also were hampered by enemies like King Philip Augustus of France and Pope Innocent III. England's foes had exhausted and defeated English forces abroad, and English taxes to pay for these efforts had taken their toll internally. In 1215, England's feudal barons compelled King John to sign the Magna Carta in the plain called Runnymede between Windsor and Staines on the 15th day of June. This document reinstated the rights of the nobility, explicitly proclaiming that the king would be bound by the law. While the document was mostly a restatement of old rights that had been violated, it nevertheless was quite striking in some of the provisions it imposed upon King John. Here the Magna Carta refers to the king using the royal we.
If we, or our justice, or our bailiffs, or any one of our servants shall have transgressed against anyone in any respect, or shall have broken some one of the articles of peace or security, and our transgression shall have been shown to 4 barons of the aforesaid 25, those 4 barons shall ask us to cause that error to be amended without delay. And if we do not amend it within a term of 40 days, the aforesaid 4 barons shall refer the matter to the remainder of the 25 barons, and those 25 barons, with the whole land in common, shall distrain and oppress us in every way in their power, namely, by taking our castles, lands, and possessions, and in every other way that they can, until amends shall have been made according to their judgment, saving the persons of ourselves, our queen, and our children.
One of those present at the signing of the Magna Carta was Robert Grosseteste, a Franciscan prelate and scholar from Oxford. Grosseteste had studied law, medicine, and theology at Oxford, and possibly at Paris. Not long after the events at Runnymede, he was appointed as the very first chancellor of Oxford University in 1221. Among his many interests, Grosseteste studied certain questions of optics. Almost nothing was known about optics in Europe, but Grosseteste had access to several classical optical works that had only recently been translated into Latin. He studied Euclid, Aristotle, and others, but he did not have the more important optical works that would become available within a few decades. Grosseteste believed that the world itself was created when a point of light diffused into a spherical form, so to him, optics was the most basic science of nature. He believed that vision requires not only radiation from a light source like the sun, but that it also requires radiation from the eye, which he called visual rays or visual species. In Grosseteste's terminology, the science of perspective examines how the so-called visible species radiate from the eye.
Perspective is the science based on visual figures, and it is subordinate to the science based on figures containing radiant lines and surfaces, whether that radiation is emitted by the sun, the stars, or some other radiant body. Nor is it to be thought that the emission of visual rays from the eye is only imagined and without reality, as those think who consider the part and not the whole. But it should be understood that the visual species is a substance, shining and radiating like the sun, the radiation of which, when coupled with radiation from the exterior shining body, entirely completes vision.
Grosseteste divided the science of perspective into 3 categories, corresponding to the ways in which visual rays are transmitted from the eye to an object seen. Some objects are seen with rays traveling in a straight line. Others are seen by reflection, for example in a mirror. Third, some things are seen through transparent media of different kinds, which here essentially means lenses. Grosseteste described the effect of lenses.
The ray reaches the object not by direct approach, but by a path of several straight lines joined at angles.
As Grosseteste continues on this third type of vision involving lenses, we should remember that his treatise was written in the first half of the 13th century, 400 years before the development of the telescope.
The third part has remained untouched and unknown among us until the present time. This part of perspective, if perfectly understood, shows us how to make very distant objects appear close, how to make nearby objects appear very small, and how to make a small object placed at a distance appear as large as we wish, so that it would be possible to read minute letters from incredible distances, or count sand, seeds, blades of grass, or any minute objects.
Grosseteste then explains in his own terms just how refraction works to bring about these magnifying effects. Roger Bacon, a Franciscan scholar at Oxford and undoubtedly a student of Grosseteste's, became the center of a movement that explicitly criticized the traditional respect for authority and custom. Bacon was hostile to any scholarly tract about the natural world that was uninformed by careful observation. He assailed those who based their opinions on the ancient masters or on pure armchair speculation. Bacon said the student of nature should base his opinion upon experiment.
He who wishes to rejoice without doubt in regard to the truths underlying phenomena must know how to devote himself to experiment. For authors write many statements, and people believe them, through reasoning which they formulate without experience. Their reasoning is wholly false.
By the time Bacon began his own work in optics, the 10th and 11th century works by Ibn al-Haytham had become available in translation, along with even more ancient works. All of these had been unknown to Grosseteste just a few short years before. Bacon now performed experiments inspired by these works and by the work of Grosseteste. Bacon, like his teacher, was confident that one day microscopes and telescopes would reveal unimagined detail about nature. Indeed, Bacon's faith in science seemed to know no bounds. He was so confident about the practical value of experimental science that he envisioned self-propelled boats and land vehicles. He even foresaw the invention of underwater boats and flying machines. Bacon's love of science attracted the attention of his superiors in the Franciscan order, and they were not pleased. The general of the Franciscan order, Saint Bonaventura, clearly expressed his own attitude toward science.
The tree of science cheats many of the tree of life, or exposes them to the severest pains of purgatory.
Bacon was called before the Franciscan authorities, criticized for his work, and placed under the surveillance of his superiors. Yet Bacon was not alone in his conviction that the experimental method is the only reliable way to investigate nature. Pierre de Maricourt, also known as Petrus Peregrinus, began a series of experiments concerning magnetism. De Maricourt eventually wrote a small book about magnetism in 1269. Here is Bacon's description of his friend.
Though others strive blinkingly to see, as a bat in the twilight, the light of the sun, he himself contemplates it in its full splendor, on account of which he is a master of experiment, and therefore he knows by experiment natural history, and physic, and alchemy, and all things in the heavens and beneath them. Indeed, he is shamed if any layman, or grand dame, or soldier, or country bumpkin knows anything that he himself does not know. Should he wish to stand well with kings and princes, he would find those who would honor him and would enrich him. Or, if he were to show in Paris by his works of wisdom all that he knows, the whole world would follow him. Yet, because either way he would be hindered from the bulk of his experiments in which he most delights, so he neglects all honor and enrichment, the more since he might, whenever he wished it, attain to riches by his wisdom.
De Maricourt built a lodestone sphere, and he examined how short pieces of iron wire behaved in the vicinity of this magnet. His research taught him that the opposite poles of a magnet attract each other, and that like poles repel. He also knew that breaking a magnet into two parts creates two magnets, each with its own poles. The 13th century was fruitful also in the study of human anatomy. Mondino de Luzzi, also known as Mondinus, conducted his own dissections in Bologna in the late 13th and early 14th centuries. He wrote a book that became the principal anatomy text throughout Europe. He described his motives for putting the book together, and they're rather typical of 13th century craftsman scholars.
As Galen, following the authority of Plato, had said in the 7th book of his Methodus Medendi, a work in any science or art is published for 3 reasons. First, for the satisfying of friends. Second, for the useful exercise of the faculties. And third, as a remedy for the forgetfulness which doth come with lapse of time. Moved by these, I have projected a work for my pupils in medicine.
Scholars in the 13th century still hated what they considered to be manual labor, and this continued to hinder scientific progress. De Luzzi and other scholarly doctors briefly renewed the practice of doing their own dissections, but this did not last long. Most of De Luzzi's successors preferred to stand aside and supervise illiterate barber surgeons who actually did the messy work. The unwillingness among doctors to get their hands dirty was supported by official church doctrine. The Council of Tours had met in 1163 and insisted that the church abhors the shedding of blood. The doctrine originally had been intended to condemn the common practice of dismembering and boiling crusaders who'd been killed in battle, a practice that had made it much easier to transport their remains home. But the scholarly doctors of anatomy were happy to apply the old hands-off doctrine to dissection in the 13th century. Along with other scientific pursuits, alchemy arose again in the 13th century. New chemicals like the mineral acids were discovered. Alchemists also began to study what they called the water of life. The water of life was not supposed to be quite as potent as another more vital fluid, the elixir of life, but it was potent enough. The water of life was first described by a writer called Magister Salernus sometime before 1167. He said it could be prepared by distilling wines and beers. In modern times, of course, we call this alcohol. Incidentally, the Gaelic term for water of life is ushcabe. This word has been passed down by the Irish to take on its modern form, whiskey. The historian Stephen Mason offers an intriguing account of how Middle Age science contributed to our modern understanding of alcohol and its effects.
The properties of alcohol appear to have been studied extensively by the monks and friars, perhaps to excess in some cases, as the possession of apparatus for distilling alcohol was forbidden to members of the Dominican chapter at Rimini in 1288. However, the monastic orders continued their studies, developing a number of celebrated liqueurs.
Alchemical theory had changed very little since its Alexandrian heyday. For example, it had long been known that vapor of mercury could impart a silvery cast to the surface of the base metals, so mercury was regarded as the spirit of silver. Indeed, mercury was widely thought to be the progenitor of all metals because of its silvery properties. Raymond Lull, a Catalonian alchemist and logician in the late 13th and early 14th centuries, developed a metaphysical theory in which mercury is the natural basis of all material things. Lull contended that God had created the world by first creating mercury, and mercury then became differentiated into all the various things in the world. Lull's influential theory eventually led to an important 16th century movement in medical science called iatrochemistry, but Lull's own fate was apparently less grand. He was an evangelistic Christian, and tradition has it that some of the Muslims he tried to convert to Christianity made sure that he became a martyr to his faith. By 1317, Pope John XXII issued a bull, that is, a pronouncement, strictly forbidding the practice of alchemy. Additionally, the universities mostly ignored alchemy and its tradition, perhaps because alchemy was far too experimental for the tastes of most scholars after the 13th century. The commitment to hands-on experiment had been a hallmark of scientific research at great European universities during the lives of Bacon, de Maricourt, and de Lutzy, but it was short-lived. By the 14th century, scholarly scientists engaged in rational discussion, not experiments. Aristotle's philosophy was now available much more widely than ever before. Albertus Magnus and Thomas Aquinas had integrated Aristotle's ideas with Christian theology about a century earlier. Aquinas, one of the most important thinkers by far in the history of Christian thought, also produced a new cosmology that required God's constant assistance to keep the heavenly bodies moving in their observed paths across the sky. William of Ockham, another Franciscan scholar from England, challenged Aquinas' theory in the 14th century. His argument is in a form that's interesting, especially in light of later developments in scientific thinking. Ockham insisted that bodies in motion do not always need continuous contact with whatever brings the motion about. For example, he insisted that projectile motion should not be understood as something that the projectile receives from an outside force. Rather, he says a projectile in motion cannot be separated from its motion.
The moving thing in such a motion, after the separation of the moving body from the prime projector, is the very thing moved according to itself, and not by any separate power, for this moving thing and the motion cannot be distinguished.
Occam cited magnets as an example of something that induces motion without physical contact. Occam argued that action at a distance is possible, and so God doesn't need immediate contact with the heavens in order to keep them moving. Occam also said it's not necessary to think that all space should be filled. In Occam's view, nothing stands in the way of the possibility that a complete vacuum exists at various places in nature. Here Occam used the impetus theory of the 6th century thinker Ioannis Philoponus, a theory lost to Europe for nearly 800 years, but recently recovered through contacts with the Arabian centers of learning. Philoponus had used the same reasoning as Occam now used to say that a vacuum might exist. For Philoponus, the Aristotelian cosmology, which was well accepted in Alexandria, was wrong. Under the influence of Aquinas, Aristotle's cosmology had again become dominant, and now Occam was again saying Aristotle was wrong. Aristotle had described a series of crystalline spheres, each containing a planet. The outermost of the spheres was supposed to be propelled by God, and the other spheres were believed also to require their own private movers. These lesser movers, responsible for the motions of the stars, the sun, the moon, and the planets, had been identified, both before the Dark Ages and by Aquinas, with various types of angelic beings. Philoponus in the 6th century, and now Occam in the 14th, used their theory of impetus and action at a distance to argue that none of these angelic beings were necessary to explain the motion of the heavens. Once the heavens had been set in motion by God, nothing more was needed. The heavens would continue to move until something interfered with their motion, thus causing them to stop. For Occam, it was achievement enough to reduce the number of principles needed to explain the planetary orbits. His analysis of motion led him to formulate the principle that physical explanation should always be as simple as possible. This principle has carried his name into the modern world. It's called Occam's razor. In a formulation given by one of Occam's more able compilers, the principle reads like this:
It is futile to accomplish with a greater number of things what can be accomplished with fewer.
Occam's colleagues at Oxford were somewhat interested in the impetus theory of motion, but it was taken up far more eagerly at the University of Paris. The Aristotelian theory of motion had said that in order to keep moving, bodies in motion must be constantly propelled by the displaced air that rushes in behind them as they move along. Aristotle thus accounted for motion by invoking the idea that nature abhors a vacuum. Jean Buridan, rector of the University of Paris, pointed out that not all motions can be accounted for by the Aristotelian approach. He observed that a spinning top, for example, rotates without changing its position, and it seemed impossible to account for its motion by the displacement of air. Furthermore, Buridan argued that if the Aristotelian view was correct, an arrow with a flattened back end should move faster than an arrow whose back end was pointed. The air would have a broader surface to push. Buridan contributed much to the impetus theory. He contended that the total amount of the impetus imparted to any object must be proportional to three things: the object's density, its volume, and its initial speed. Joining Philoponus and Occam, Buridan insisted that if we understand motion to involve impetus, we have no need to believe that angels move the heavenly spheres.
One cannot read in the Bible that there exist intelligences charged with giving the celestial orbs their proper motions. It is then permitted to show that there is no necessity of supposing the existence of such intelligences. One might say, in effect, that God gave each celestial orb an impetus, which has kept it going since.
In the 1350s, Albert of Saxony took up Buridan's position. Albert appears to be the first to have distinguished clearly between three different types of motion. His distinctions would later become a central part of Galileo's work in the early 17th century. First, Albert of Saxony thought it important to consider separately what he called uniform motion, where an object moves with a constant speed. Second, there is difform motion, where the speed of an object varies in a smooth and regular way during the course of its motion. Finally, Albert describes irregular motion, where the motion changes erratically. Albert of Saxony also argued that objects falling under the influence of gravity will not increase their speed indefinitely. He said that they will eventually reach a limiting speed. He came to this conclusion by comparing the resistance in air, in water, and in an imaginary vacuum.
A heavy body is moved through air more quickly than through water, because air is subtle and resists less than water. And since in a vacuum there would be absolutely no resistance, it seems that a heavy body ought to be moved most easily in a vacuum.
As an object moves faster and faster under the influence of gravity, Albert said the resistance of the air will tend to limit the additional amount of impetus that can be imparted to it. Yet the single most important advocate of the impetus theory was the French prelate Nicole d'Orem, known in English as Nicolas Orem. Aurème became the Grand Master of the College of Navarre at the University of Paris in 1356. He also privately instructed the first French Dauphin, Charles, who later became King Charles V of France. Charles was a great patron of the arts and of learning during his reign, perhaps because of the influence of Aurème. In discussing motion, Aurème brilliantly conceived a scheme in which various types of motion can be represented on a two-dimensional graph. First, he represented the path of any arbitrary object by drawing a horizontal line. The beginning of the path is at the far left, and the end of the path is at the far right. To this simple scheme, Aurème added the convention that, at any point along the horizontal path of the moving object, its speed can be plotted as another point along the vertical dimension. As historian A.C. Crombie notes, Aurème's mode of diagramming motion in the 1350s anticipated René Descartes' development of analytic geometry almost 3 centuries later.
There is in his work no systematic association of an algebraic relationship with a graphical representation. Nevertheless, his work was a step towards the invention of analytical geometry, and towards the introduction into geometry of the idea of motion, which Greek geometry had lacked.
The different types of motion described by Albert of Saxony appeared as different lines or curves in Aurème's graphs. An object moving in uniform motion, say at 1 foot per minute, is represented by a straight horizontal line above the baseline. An object moving in difform motion with increasing speed would be represented by a straight line sloping upward to the right. One moving with decreasing speed would slope downward to the right. Finally, an object in irregular motion, or as Aurème put it, in deformly deform motion, would be represented by a curve above the baseline. If we close in the right and left sides of the graphs, then uniform motion will be represented by a rectangle, deform motion will be represented by a triangle, and irregular motion will produce a figure bounded on the top side by a curve. This method of representation would later be very important in developing the science of motion in the 16th and 17th centuries. Aurème also thought his method of configuration, as he called it, could describe all phenomena and bring them within the category of natural science. He believed that even occult or magical processes could be understood by using the graph to discern previously unnoticed qualities within the objects involved. Aurème described which questions might be answered using his method.
Why sounds of certain musical instruments are harmonious? Why strings of wolf-gut cannot sound in concord with those of sheep-gut? Why a tin vessel, although more dense than a wooden one, heats more quickly? Why some human families are unharmed by poison snake bites? Why man and dog have a natural friendship? Why sheep and wolves have natural enmity? Why theriac is an antidote to poison? Why the laurel tree and the eagle are never struck by lightning? Why the diamond is broken by hot goat's blood, though not by iron or fire?
The 13th century impetus theorists, though a minority movement, claimed adherents among important figures in major universities. Their influence lasted into the 16th century. Some of the positions favored by Occam, Buridan, Albert of Saxony, and Aurème bordered on what the Church considered heresy. Occam got into a great deal of trouble. He was detained in Avignon from 1324 to 1328 on charges of heresy. He fled to protection in the royal court of Louis of Bavaria before the investigations could be completed. There he wrote a series of scathing condemnations aimed not only at Pope John XXII, but also at his Avignon successors. Occam contended that the papacy had become tyrannical in violation of God's law.
As Christ did not come into the world in order to take away from men their goods and rights, so Christ's vicar, who is inferior to him in power, has no authority or power to deprive others of their goods and rights.
Occam's cause was not won in his lifetime. He died in 1349, probably of the Black Plague. The impetus theory incorporated many heretical doctrines. One was that the stars appear to move across the night sky because the earth rotates on an axis, not because the heavens rotate around a stationary earth. Orem proclaimed most clearly and emphatically that the earth rotates, and he offered a form of reasoning that would play the most crucial possible role in the development of science. He observed that the competing theories could not be distinguished observationally.
No experience whatsoever could prove that the heavens rotate daily, and not the earth.
Orem is saying here that wherever two competing theories have precisely the same observational consequences, there can be no good reason to insist on the truth of one and the falsity of the other. This maxim was wielded with great force by later empirical scientists. The impetus theorists also favored the idea that the universe is infinite. They believed that other worlds, like the Earth, may be found somewhere in the infinite expanse of the cosmos. The most forceful expression of this view on infinity was offered in the 15th century by Nicholas of Cusa. Nicholas represents the very boundary of the modern period, both in time and in point of view. He was born as Nicholas Crifts, or Krebs, in Germany. This fisherman's son pursued his education as avidly as any nobleman at the most prestigious institutions in Europe: Deventer, Heidelberg, Padua, Rome, and Cologne. He came to be known in the scholarly world by his Latinized name, Nicolaus Cusanus, and in 1448 he became a cardinal in the Roman Catholic Church. Nicholas's standing in the Church was impeccable. He even served as a distinguished papal legate, traveling through Europe as both preacher and diplomatic negotiator for the Holy See. Yet for all his recognition as a powerful representative of the status quo, Nicholas of Cusa's revolutionary views on the universe were astonishing. First, Nicholas agreed that the apparent motion of the stars is caused by the Earth's rotation. He also agreed that the universe has no outer boundary, although he was not quite prepared to say that it was literally infinite. Nicholas preferred to say that the universe is interminate.
So the world is not infinite, yet it cannot be conceived as finite, since it has no limits between which it is confined.
Nicholas said that if the universe is unbounded, then the Earth cannot be at its center. Indeed, the universe simply has no center. He said that another way to understand the situation is to conclude that every place in the universe is as much the center as every other. From these considerations, Nicholas drafted a remarkably sophisticated theory about the relativity of space, of motion, of all things in the universe. Nicholas thus offered, in the 15th century, a line of reasoning that was delightfully ahead of its time. Albert Einstein was to employ very similar reasoning almost 5 centuries later in developing his famous special and general theories of relativity. But Nicholas's revolutionary insights included still more. He began to criticize the traditional Aristotelian point of view that the heavens are more perfect than the earth. He argued that such knowledge is not available to human beings. He said that the heavens are probably made up of the 4 Aristotelian elements, the same elements that make up objects on earth. He believed there can be no good reason to deny the possibility that the entire cosmos, stars, planets, sun, moon, and comets, are all of a piece, with no part superior to any other.
It is not possible for human knowledge to determine whether the region of the earth is in a degree of greater perfection or baseness in relation to the regions of the other stars, of the sun, the moon, and the rest.
Nicholas then followed the reasoning all the way through. If the earth is not the center of the universe, then gravity is not a tendency to move toward the center of the universe, as Aristotelian theory claimed. Nicholas postulated that every heavenly body is something like the earth, and that each such body is a gravitational center unto itself. Finally, he explicitly suggested that the other heavenly bodies might very well be inhabited, just like the earth. These views were not yet dominant at the close of the Middle Ages. The real battle of ideas was yet to come, a battle that occasionally would become bloody. The Spanish Inquisition undertook to save the souls of those it accused of heresy. Those who believed in free inquiry now had to fight against the old established views. The introductory skirmishes had already occurred well before 1543, when Nicolaus Copernicus published his idea that the sun is at the center of the cosmos. The Copernican view came to be championed by such men as Giordano Bruno, Johannes Kepler, Galileo Galilei, and René Descartes. Yet many of their arguments had already been advanced by the likes of Albert of Saxony, William of Ockham, and Nicholas of Cusa. The Middle Ages are remembered as a time of stagnation in the intellectual progress of mankind. But, like periods of sleep in humans, it may be that these 10 centuries, from the fall of Rome to the European Renaissance, represented a period of stock-taking. Perhaps it was a time needed to build reserves for the dramatic developments that followed. Whatever else may be said about this era of slow growth, this age of magic and worship, it is important to remember that it deserves some credit for the world that later sprang forth. Our brave new world was not just a triumph over the Middle Ages. It was in many ways its product, and to that extent, then, so are we.
We hope you have enjoyed this presentation of Medieval Science by Knowledge Products. The script for this presentation is by Dr. Jack Sanders. The script is edited by Jack Summer and Mike Hassel and produced by Pat Childs. Local characterizations are by Mario Bacigalupo, Dan Church, Patricia Childs, Rob Daniel, John Fraser, Travis Hardison, Mike Hassel, Joe Keenan, Risa Ordubadian, and John Sherberg. Music is by Ron Christie, Christie Productions, recorded at Sync Sound and Archer Productions. This material may not be copied in whole or in part without the written permission of the copyright owner. Copyright 1992 by Carmichael & Carmichael Incorporated. This presentation on Science and Discovery is a part of the Audio Classics series. This continuing series of audio presentations discusses the great ideas and events of history in their historical and intellectual context.